Right. Hello, everybody. I'm Andrea Malchiodi, and I'm the current director of the Giorgi Mathematical Research Center. So I would like to welcome you to the Pisan Workshop in Geometric Analysis, which reached the 4th edition. So congratulations to the organizers. I'll just speak for a minute to describe some brief history and activities of the Giorgi Center. It was founded about 20 years ago, formally as a research laboratory of Scuola Normale Superiore, and the mission is to be like a gathering opportunity for the mathematical community in Pisa to meet. So the community, apart from Scuola Normale, includes the University of Pisa and also a small group from Scuola Superiore Sant'Anna. And these two institutes, especially the former, contribute crucially to the activities of the center. So since the foundation, the activities have been mostly workshops, schools, intensive research periods. And recently we restarted a colloquium series, which is named to Ennio De Giorgi. We have visiting positions of two types, short-term visiting positions to perform research in pairs or group, and 2 years postdoctoral positions. So that's all I wanted to say, and I just conclude thanking the organizers for bringing up this high-quality event, and also to the staff of the center for their constant and valuable support. Thank you.
Thank you, Andrea. First of all, I want to thank Centro De Giorgi for the opportunity to have this conference here for the first time. The very beginning of this conference was during the COVID period, and with Mattia, as at that point was a postdoc here at Centro De Giorgi, we decided to organize an online meeting because it was a period in which there was no contact among us, and we wanted to give the opportunity to young people in geometric analysis to give a talk and to have the opportunity to present their result. And after that, we have decided that the meeting was successful, and we wanted to proceed with in-presence events. Why in Pisa? Because we strongly believe that Pisa is a good center for geometric analysis. And why for young PhD student and young postdoc? Again, because we believe that there is a very strong group, a very active group of young people in geometric analysis in Europe and around, in Italy and around Europe. And we want to gather here people that have the common interest of working in this very beautiful subject. Again, I want to thank the Centro, and I want to thank all of you, because people that were here also in the other events, as they realized that the workshop is such nice workshop because of the participant. Clearly, I want to thank already all the speaker, because without the speaker it would be totally impossible to have this very nice event. But the center of the workshop is really the collaboration between speaker and participant and young mathematician. Thank you to all of you, and we should start with the first speaker. So it's a great pleasure for me to introduce our first speaker, Daniele Semola from ETH Zurich, that is going to speak about Ricci curvature, fundamental groups, and the Milnor conjecture. Please start.
Thanks, Alessandra. Thanks for the introduction, and thanks to all the organizers for the invitation. So I'm going to be speaking about Ricci curvature, fundamental groups, and the Milnor conjecture. And let me start by recalling what the conjecture said. So this talk is going to be about the conjecture that John Milnor raised in 1968. And the conjecture asked whether it was true or not that given a smooth, complete, and dimensional Riemannian manifold, and all Riemannian manifolds are going to be smooth and complete for the rest of the talk, unless otherwise stated, whether it was true or not that if you assume that the Ricci curvature of the manifold is non-negative, then the fundamental group of the manifold should be finitely generated. And this talk is meant to be a kind of rough overview around the developments around this conjecture. And more in particular, I would like to follow some recent joint work, with Elia Broè from University Bocconi, Milan, and our neighbor from Northwestern, where we construct a family of counterexamples to the Milnor conjecture. More precisely, our main result is the following. You start from any subgroup of the rational numbers modulo the integers, which is indeed the subgroup of the circle. And for any such group, we build a smooth, complete Riemannian manifold, which is 7-dimensional, has non-negative Ricci curvature, and it has fundamental group isomorphic to the given group you were starting with. So in particular, let me make the obvious remark that in the family that I described in the statement, there are indeed groups, discrete groups, which are not finally generated. And in particular, we are building up a family of counterexamples to the Milnor conjecture. Okay, so here is a brief outline of for the rest of the talk. There is going to be some background on the relationship between Ricci curvature lower bounds and fundamental groups, more in general. I would like to briefly mention some of the positive results that have been obtained in the last, say, 50 years or so. And then in the second part of the talk, I will focus on the topological construction of the counterexamples, and then I would like to discuss more in detail some of the, I would call them geometric steps, where you try to endow the topological manifold, the differentiable manifold that you have built with a metric with non-negative Ricci curvature in order to contradict Milnor's conjecture. And then, if I have still a couple of more minutes, I will mention a few open questions related to this conjecture of Milnor. So let me start. My first goal is to try to convince you that indeed there is some hope that the Ricci curvature lower bound can lead to some control on the fundamental group. And I will start from the case where one assumes that the Ricci curvature lower bound is strictly positive. So you have a manifold which is smooth complete, and you assume that the Ricci curvature is bounded below by a positive, strictly positive constant. And then a theorem due to Bonnet in the two-dimensional case and to subsequently due to Myers in 1941 says that if you assume that such a manifold satisfies such a lower bound, for the sake of normalization, I'm just going to assume that Ricci is bounded from below by n-1, then the diameter of the manifold is bounded from above by pi. In particular, you get the highly non-trivial statement that the manifold is compact. And now, getting the control of the fundamental group is almost straightforward. The reason being that you can start from a manifold with Ricci strictly positive, bounded away from 0. You look at the universal cover. Ricci is a completely local quantity, so also the universal cover is going to have the same lower bound on the Ricci curvature. You apply Bonnet-Myers theorem, you get the universal cover is compact, and this is telling you that the fundamental group, not only it is finally generated, but it is indeed finite. Okay, so this is in order to convince you that Ricci can indeed lead to some control over the fundamental group. Let me pass to the case where Ricci is assumed to be non-negative, and we start to consider non-compact manifolds. So one of the fundamental tools in the study of manifolds with non-negative Ricci curvature, and more in general in the study of manifolds with the Ricci curvature lower bound, is the so-called Bishop-Gromov volume monotonicity formula, which in the case we care about, so in the case where Ricci is non-negative, is giving you a monotonicity of the scale invariant volume ratio. So you pick the volume of any ball, you divide it by the volume of the Euclidean ball, and the Bishop-Gromov theorem is telling you that this quantity is non-increasing. Okay, very well. So in the very same paper where he raised the conjecture about finite generation of fundamental group, Milnor proved the following theorem. He proved that if you, by using the Bishop-Gromov volume monotonicity, he proved that if you stare at a Riemannian manifold with non-negative Ricci curvature, then the following is true. If you look at any finitely generated subgroup of the fundamental group, this discrete group is going to have polynomial growth of growth order less or equal than n. Okay? Polynomial growth means that if you fix a family of generators and you count how many distinct elements you can write with the, say, little r letters from this family of generators, this is growing like a polynomial in R into the number of letters that you want to use. Okay, and let me draw the almost obvious conclusion that this is already ruling out some possible discrete groups as fundamental groups of a manifold with non-negative Ricci. Indeed, for instance, if you start from the free group with two generators, it's an easy exercise to check that this is not a group with polynomial growth, even though it is finitely generated. And in particular, Milnor's theorem is telling you that this is not a fundamental group of a manifold with non-negative Ricci. And on the other hand, another example is if you start from, if you wonder whether z to the n+1 is the fundamental group of a n-dimensional manifold with non-negative Ricci, then again, another easy exercise is to check that the growth of this discrete group is indeed polynomial, but the growth rate is n+1. So it's the same as the dimension of the group. And Milnor's theorem is telling you that this is not a possible fundamental group of such a manifold. Okay, very well. Then the story goes on with an abstract and celebrated theorem due to Gromov in 81, telling that if you start from an abstract finally generated group, discrete finally generated group, which is of polynomial growth, then such a group is virtually nilpotent. Virtually nilpotent means that it has a finite in the subgroup, which is nilpotent. And if you apply the combination of this theorem of Gromov and the previous theorem due to Milnor is telling you that each finally generated subgroup of the fundamental group of a manifold with non-negative Ricci is indeed virtually nilpotent. So it is giving you some structure on the possible finally generated subgroups of the fundamental group of a manifold with negative Ricci. And I think, so this is all about abstract groups, let's say. And I think it was Gromov itself to ask the question whether in the case of fundamental groups of a manifold with non-negative Ricci, one could quantify his statement. And in particular, he wanted to quantify both the number of possible generators of such finally generated subgroups and let's say the nilpotency length coming from his abstract theorem about general discrete groups. And as I was saying, this stimulated a lot of work. Let me just mention here, let me be very brief and mention the work of Fukai Yamaguchi in 92 and Kapovic, Petruni, and Tushman subsequently. And let me focus on the actual statement in the case we care about, the case of non-negative Ricci curvature. The statement in this setting is due to Kapovic and Wilking in 2011, and it says the following. So you fix a dimension, little n, then there exists a constant C of n, which is universal, it's only depending on the dimension, such that the following property is solved. So you start from a manifold with non-negative Ricci. Then, if you look at the fundamental group, this discrete group is gonna contain a nilpotent subgroup with index uniformly bounded by the constant C of n. And this subgroup is very nice to the effect that it has the following two properties. If you look at any finally generated subgroup of this big subgroup capital N, then the number of generators of this subgroup can be bounded by C of n, a universal constant, and you can also bound the nilpotency length of any such subgroup. This is bounded above by the dimension. Okay, let me draw another conclusion from this. Let me illustrate that this is again ruling out some possible fundamental groups in this class of fundamental groups of manifolds with dimension n and Ricci bounded from below by n. Indeed, let's stare z over 2z raised to the power capital N, where capital N is, let's say, arbitrarily large. And I claim that this is not, for n sufficiently large, this cannot be the fundamental group of a manifold which is n-dimensional and thus Ricci non-negative. The reason is that this group is finite. So Milnor's sole theorem was not able to rule this out as a fundamental group of an n-dimensional manifold with a negative Ricci. But however, Kapovic and Wilkie's theorem is telling you that the number of generators of this group, which is finite indeed, must be bounded by C of n. And if you pick capital N large enough, this is telling you that this cannot be the fundamental group of a manifold with a negative Ricci, which has dimension little n. Okay? And of course, if you have any questions or comments, feel free to interrupt me at any time. Okay, the last, say, general result related to the background concerning the relationship between Ricci curvature lower bounds and fundamental groups is known in the literature, it has been known in the literature as Wilkins reduction. And very roughly speaking, what Wilkins proved was that if one was looking for a counterexample to the Milnor conjecture, one could restrict indeed to abelian fundamental groups. So the precise statement is the following. You pick any manifold with a negative Ricci, then we can prove that the fundamental group of such a manifold is finally generated if and only if any abelian subgroup of the fundamental group is finally generated. Okay? Very well. And let me make the obvious observation that the fundamental groups that we build indeed do verify all the expected restrictions coming from the previous theory. So in particular, for any subgroup of Q mod Z, the rationals modulo the integers, you can easily check that this is going to be abelian. And moreover, not only you have uniformly finitely generated subgroups, but any finitely generated subgroup of any such group is going to be cyclic. So it's going to be finitely generated with one generator. Okay? This is an easy algebraic verification. So let me go into the second part and discuss some of the previous developments about finite generation for fundamental groups of manifolds with a lower curvature bound. So first statement that I would like to discuss is about the case where you strengthen the lower curvature bound from a Ricci curvature lower bound to a sectional curvature lower bound. And you make the assumption, so the stronger assumption, that the sectional curvature is non-negative. In this case, a theorem going back to Gromov in 78 tells you that the fundamental group must be finely generated, and Gromov was also able to compute an explicit bound on the number of generators that you need in order to generate any such fundamental group. So it gets the explicit constant 3 to the n. Let me make the comment that if you don't care about the quantitative bound on the number of generators, on the number of generators, finite generation was indeed already known since the work of Chiger and Gromolo on the Soul theorem a few years before. Okay, and let me also recall that in dimension 2, a stronger rigidity, a stronger basically diffeomorphic characterization of possible manifolds with non-negative Gaussian curvature in dimension 2 was more classical, and it goes back to work of Convossen in 1935. So given this theorem about manifold with non-negative sectional, the first non-trivial case to analyze for the Milnor conjecture is a three-dimensional case, and it turns out that this was already really subtle. Okay, so this remains open until the work of Liu in 2013, and Liu, again, as in the two-dimensional case, proved indeed a much stronger diffeomorphic classification of manifolds with non-negative Ricci curvature. His statement is the following: you start from a non-compact, complete, free manifold with non-negative Ricci curvature, then one of the following two possibilities must occur. Either the manifold is diffeomorphic or free, or it has a cover which splits a line isometrically, in which case the cross-section is going to be a manifold with non-negative Gaussian curvature, and therefore you're back in the previous case. So you get indeed that the manifold must have non-negative sectional curvature. And an almost elementary corollary, descending from this diffeomorphic characterization theorem, is that indeed the Milnor conjecture holds true when the dimension is equal to 3. And let me make the observation that the case of Ricci positive everywhere, not bounded away from 0, but positive, was previously considered with similar techniques by Shane and Yao back in 1982, but the case of non-negative Ricci remained open for more than 30 years. And let me also point out that more recently, in 2020, Pan found a different argument to prove just a part of the statement concerning the Milnor conjecture in dimension 3. So I would say more elementary proof, but he's only able to get to the statement of finite generation for fundamental groups of manifolds which have dimension 3 and have non-negative Ricci curvature. So the next kind of developments that I would like to review are those related to the volume growth of manifolds with non-negative Ricci curvature. So this slide is going to be about statements concerning finite generation of fundamental groups in the case where you make assumptions on the possible rate of growth of the volume of balls for the manifold with non-negative Ricci. So let's come back to one of the very first slides. So we have Bishop-Gromov volume monotonicity. And one of the corollaries of Bishop-Gromov volume monotonicity is that if you have an n-dimensional manifold with non-negative Ricci, then the volume growth is going to be at most the volume growth of the Euclidean space with dimension n. And so one might wonder what happens in the case where you make the assumption that this volume growth is maximal. So the balls have volume which grows like r to the n, where n little n is a dimension. And a statement going back to work of Lee in 86, and later reproved with a different argument by Anderson in 1990, is that if you have a manifold with non-negative Ricci, and the volume growth is indeed maximal, so one says in the literature that this manifold has Euclidean volume growth or maximal volume growth, then not only you get finite generation, but you get that the fundamental group is finite. Okay? One might wonder what happens at the other extremum of the scale of possible volume growths. So let me first point out that there is another extremum for the scale of the possible volume growth rates of volume growths. Indeed, Calabi and independently Yao proved that if you have a manifold with a negative Ricci curvature and it is non-compact, then its volume must grow at least linearly. And a statement due to Sormani in 2000 is that if you are, as I was saying, in the other extremum of the scale of volume growth, so you have a manifold with a negative Ricci, it is non-compact, and you assume that the volume growth is minimal, so it is linear, then the pi1 is finitely generated. Okay? And the model that one should have in mind is the trivial example of the cylinder. Okay? In that case, you cannot get finiteness for the fundamental group, but you still get finite generation. Okay? Any questions or comments? Okay. So if not, let me start with the second part of the talk. I would like to briefly describe, as I was saying, the differentiable structure of the manifold of the family of manifolds that we build in order to contradict Milnor's conjecture, and then to focus on some of the geometric steps of the construction. But before then entering into the details of the construction, let me address a very basic question. So you might ask whether it is indeed the case that manifolds with the fundamental groups which are not finitely generated but satisfying the restrictions coming from the theory do indeed exist. And the answer is that they do exist. And the classical example in this regard is the so-called dyadic solenoid complement. So a theorem going back to Steenrod in 1943 says that you can find a free manifold with fundamental group which is isomorphic to the dyadic rationals. So those are the rational numbers with denominator which is a power of 2. Okay, so and let me point out that this is indeed one of the fundamental groups that you were able to catch in our construction of counterexamples to the Milnor conjecture. So from the algebraic point of view, this is perfectly compatible with the known restrictions, but still the construction is ugly non-trivial. Okay, and for the Steenrod example, I mean. Okay, and Steenrod credits Vietoris for the idea. If you have never seen such an example, maybe you might have seen another strange example of free manifold, let's say, which is the so-called Whitehead manifold. So in the 40s, I believe there was the conjecture that any open contractible free manifold should be homeomorphic to R3, and the Whitehead manifold is a counterexample to this statement. So it is a free manifold which is open, contractible, but it is not homeomorphic to R3. And let me make the comment that some of the ideas that go into the construction of the Whitehead manifold are indeed very similar to the ideas that go into the construction of the free manifold with the dyadic solenoid complement. Okay, and let me also make the comment that up to the work before the work of Liu that I mentioned before in the previous slide in 2013, the dyadic solenoid complement, so the very first, let's say, algebraically compatible manifold for a possible counterexample was indeed a potential Milnor counterexample. So people were not able to rule this out, this explicit free manifold out from being having the possibility that it had the manifold a Riemannian metric with non-negative Ricci curvature. And this is discussed in a beautiful survey by Shen and Sormani going back to 2006. To conclude this brief parenthesis about general topological manifolds with infinitely generated fundamental groups, let me also point out a statement which I believe is folklore. I'm not sure how to attribute it to. And the statement is that if you are allowed to raise the dimension, and if you are allowed to go to dimension phi, then something much more general is true. And the statement is that any countable group is the fundamental group of a 5 manifold. Okay? So next, let me enter into the construction of the counterexample. And first, I would like to give you a very rough, imprecise, but still geometrically meaningful picture about what the counterexample should look like. Okay, the geometry of the counterexamples, all the counterexamples in the family, mimics somehow that of a fractal snowflake. And this kind of similar behavior is required in order to make compatible two competing statements. So first, we would like to get a counterexample to the Milnor conjecture. So we would like to get a manifold with infinitely generated fundamental group. On the other hand, the algebraic restriction, let me call it local uniform finite generation, coming from Kapovich-Wilking. So the statement that if you look at any finitely generated subgroup of the fundamental group, the number of its generators cannot grow as much as you like. So it's uniformly bounded. This is a strong restriction on the geometry of the example that you're able to build. So these two are competing goals, and those are the competing goals that force you to put a kind of similar geometry onto the counterexamples that we are going to build. Okay. So let me start with the construction. We are not actually going to build the manifold itself. We are going to build the universal cover of the manifold of the counterexample to the Milnor conjecture. So we would like it to be a simply connected, smooth, complete Riemannian manifold with non-negative Ricci curvature. There is going to be a fixed point, and we would like to endow this smooth, complete Riemannian manifold with non-negative Ricci curvature with an action by isometries of the algebraic group gamma that we fixed at the very beginning of the construction. So gamma is any subgroup of the rationals modulo the integers. You can think about the rationals modulo the integers or the dyadic rationals modulo the integers, if you prefer. Okay, the construction is going to be inductive. And let me set up the stage with some algebraic preparations. So we fix our subgroup of the rationals modulo the integer. And we are also going to fix a sequence of radii going to plus infinity and going to plus infinity very fast. And those are going to be meaningful radii. I'm going to comment later on the meaning of this radii in the construction. And then at the algebraic level, it's easy to check that any such group, any such discrete group, can be written as a nested union of subgroups, which are cyclic. So they are finite. You can easily check that if they are finite, they are cyclic. And moreover, we are going to ask that this sequence is a nested sequence and it's exhausting all the algebraic group. So you're viewing the group as a union of increasingly dense subgroups, let's say. And as I was saying, all these finite subgroups into the circle, they are going to be generated by just one guy. I'm going to denote these discrete finite subgroups by capital gamma I, and I'm going to denote the generator of these finite cyclic subgroups by little gamma I. And another elementary verification is that there is a simple relationship between the generator of the group capital gamma I and the next generation generator coming in. So you can always find the power of the new generator, which gives you the old generator. This is all easy. You can easily check if you study the picture of the circle. Okay, what's the meaning of what's the relationship between the finite subgroups exhausting my group gamma and the geometric scales that are denoted by little ri? So what's going to happen for the counterexample is that the finite subgroups capital gamma I are going to be local fundamental groups of the n counterexamples. So local fundamental groups means that they're going to be isomorphic to the subgroups of the fundamental group of the counterexample generated by either loops with the length smaller than liter I, Ri, or if you prefer staring at the universal cover, these are going to be the subgroups of the fundamental group, which is infinitely generated. These are going to be the finally generated subgroups of the fundamental group generated by isometries that displays the base point less than the given geometric scale liter Ri. There are going to be two, let's say, dual pictures. One is going to be a global picture on the shape of the counterexample, and the other picture, which is the one that we use in the construction, is going to be an inductive picture. And from the inductive constructions, what we are going to do is we are going to turn these finite subgroups nested one into the other into a sequence of, let's say, very roughly speaking, manifolds with all the properties that we need nested one into the other. And while we go along the inductive construction, we are going to extend the action of the groups one generator at a time. So for the induction, we are going to build a sequence of manifolds, which are going to be, let's say, portions of the universal cover of the n guy. They're going to be smooth, complete. They're going to have a Riemannian metric with non-negative Ricci curvature, and they are going to be simply connected and endowed with the free isometric group action by the group capital gamma I. Okay? Let me now go on with the construction. The first thing we are going to do is we are going to build a tree as a very, very rough approximation of the shape of the universal cover of the counterexample. So the tree is going to build as follows. So we are going to fix a bunch of half lines. These half lines are going to be indexed by the elements of the group capital gamma. Now, so you have a sequence of disjoint half lines, and we are going to collapse some branches of the half lines to get a tree. And in order to do so, we need to define an equivalence relationship on the cross product group gamma cross the half line. And the equivalence relationship is defined in the following way. You get two pairs, little gamma little t and little gamma prime little t prime, and I stipulate they are equivalent provided the difference gamma to the -1 gamma prime belongs to the one of the groups, these defined subgroups in the nesting, capital gamma I, and say the radial coordinate of the guy, they are both equal and they are greater or equal than the geometric scale where the capital group, the group capital gamma I kicks in. Okay, there is going to be a picture in the next slide. Let me first make the comment that there is a trivial action of the group on the cross product in the displayed formula. So capital gamma acts on the cross product by multiplication on the first factor, trivially, say, and this action passes to the quotient. So there is an induced action of the group gamma on the tree that I'm gonna show you in the next slide. Okay, so the picture is of the tree. The bad picture of the tree is the following. So the tree, you should think about the following. The tree ends at the bottom where there is a layer of points indexed by the group gamma. Those were the starting points of the half lines that we mentioned at the starting point of construction of the tree. So before collapsing all the bunch of portions of the half lines, you get all the disjoint half lines, and the equivalence relationship is collapsing them down. So at the bottom, you get the layer of points indexed by gamma. While you go up, the tree continues forever on the top of the slide. Okay, and while you go up, the layers of points are going to be indexed by quotients of the group. So those are going to be indexed by gamma mod gamma j minus 1, and you go on. Okay. Those on the left, they are the integer, the parameters kappa j that we introduced in one of the previous slides. So this is the exponent, such that when you raise the generator little gamma j at the exponent kj, you get the generator of the previous subgroup. And you should think of them about the number of branches getting into one of the new vertices of the tree while you move along. Okay, and that's it about the picture of the tree, giving you a rough approximation of the universal cover of the Riemannian manifold M tilde that we want to build in the end. Okay, any comments or questions? Okay, if not, our next goal is to pass from the tree, so this very, say, discrete looking, one-dimensional looking object, to the 7-dimensional manifold that we want to build, that we want to have at disposal at the end. So let me discuss first the global picture that you should have. So for the global picture, the idea is that you start from the tree, and then what you do is you replace each vertex of the tree with a copy of a free sphere across a 4-disk. So those are differentiable manifolds, and there is going to be boundary. And the boundary of any such guy, let me make the comment that this is going to be diffeomorphic to a copy of S3 cross S3. Okay, so there is the boundary of the 4-disk, which is an S3, and you cross it with the copy of the free sphere that you crossed the manifold for at the very beginning. So for the global picture, you pick any vertex in the previous slide, and you replace it with a copy of S3 cross D4. Those are the meanings of the vertices, and now each edge is going to correspond to a gluing along boundary components. And what happens more in detail is that a copy of S3 cross D4, which has boundary S3 cross S3, as I was saying, is glued into another copy on the upper layer by the following procedure. So you get a copy of S3 cross D4, which is in the upper layer. You go in the 4-disk, you remove, let's say, kj, or let's say one copy of a 4-disk from the big 4-disk. It comes with a cross factor, which is an S3. This is going to have a boundary, which is S3 cross S3. So this is diffeomorphic to the boundary of the new guy that you want to glue in. And you just need to decide how you glue the two boundaries together. Okay, that's the global picture. What about the inductive construction? So for the inductive construction, as I was saying before, we are going to build a sequence of manifolds that I denoted by tilde mj. And what happens in the inductive construction is that when it comes to time for the inductive step, you want to add the new copy of S3 cross D4 on the top of a bunch of copies of the manifolds built at the earlier steps of inductive construction. So what's going to happen is that it's not a priori clear that these guys are diffeomorphic to a 4-disk cross a free sphere, but they are going to have an end, which is diffeomorphic to an annulus inside S3 cross D4. And in particular, it has a boundary, which is diffeomorphic to S3 cross D4. Okay, so what happens is that you add on the top of that a new guy diffeomorphic to S3 cross D4. You pluck out some balls, and you glue in, instead of gluing in copies of S3 cross D4, what you do is you glue in copies on the ends, you glue in copies of the manifolds that you build at the earlier steps of inductive construction. So here is the picture. This is the new guy that you want to diffeomorphic to S3 cross D4 that you want to add on top of the old guys that you build. And those are the old guys. For this inductive step, kj is equal to 4. And so the goal is to glue in 4 copies of the manifold M tilde j minus 1 that you build at the earlier steps of inductive construction. You want to glue those into a new copy of S3 cross D4. How does it goes? So you look at the 4-disk, you pluck out 4 small balls. They are going to be arranged symmetrically. They are going to be arranged along. So this is going to be the construction is going to be symmetric, and the reason is going to be clear in a second. So you pluck out 4 copies of the 4-disk. They come together with the boundary component S3. So the boundary is diffeomorphic to S3 cross S3. And as I was saying, those guys, they are not 4-disk cross S3, but they have an end which is diffeomorphic to an end in that guy. And therefore, it has a boundary component which is S3 cross S3. And now, in order to complete the construction at the diffeomorphic level, I just need to specify how I want to glue in the boundary into the boundary. Okay? So you don't at this step you are creating boundary, and the boundary is coming from this boundary of the 4-disk cross the free sphere. So the new manifold has the new manifold, which is going to be m tilde j, let's say, is going to have a boundary component which is S3 diffeomorphic to S3 cross D4. The idea is that at each of the inductive steps there is boundary, but then you are going to morally take the limit and the boundary disappears. Okay? Any other questions? Okay. And also notice that the 4 disk, if you forget about the boundary and you just stare at the interior, this is diffeomorphic to R4. And so if you don't care about the boundary, this is indeed giving you an open manifold, let's say. So the boundary disappears if you don't care about it. Okay? Okay. So now part of the non-triviality of the construction comes from this gluing diffeomorphism between different boundary components. So my next goal is to specify, illustrate you why this gluing diffeomorphism needs to be non-trivial. And in order to do so, I need to discuss some preliminaries on the action, because remember that we want to endow our manifolds in inductive construction, but in particular the end manifold, we want to endow it with an action, with the free action of the group gamma. Okay, so that was the discussion about the differentiable manifold, but we need an action of the group on this manifold, and the non-triviality of the gluing diffeomorphism is going to come from the choice of the action of the groups gamma j onto the inductive manifolds. Okay, so let me discuss a few preliminaries on the action. Let me recall that there is the well-known observation that there is a free circle action on the free sphere, which is the action inducing the so-called Hopf vibration. So key for us is that the following statement: there is a free action, a circle action on the free sphere. Okay, and a trivial consequence of this is that you can stare at the product of 2 free spheres, and there is a 2 torus action which is free on this product of 2 free spheres. So the first circle is acting by, let's say, Hopf rotation on the first S3 factor. The second circle in the 2 torus is acting by Hopf rotation on the second S3 factor. And again, trivial consequence: you can fix a pair of integers into Z cross Z, and a piece of terminology I'm going to denote by AB Hopf action, the induced S1 action by the homomorphism embedding an S1 into a 2 torus by rotating with speed A in one component and speed B in the other component. So this AB Hopf rotational action is going to be a circle action on the product of S3 cross S3, which is going to be rotating with speed A on the first free sphere and rotating with speed B on the second free sphere. And let me make the elementary observation that if A and B are coprime, the action that you get, the circle action that you get, is going to be free. And of course, freeness is going to be important for us because we want to build a fundamental group action. So it must be free. Okay? So those were the preliminaries on the shape of the action, let's say. And now let me come to the description of the action of the group gamma onto the manifold that we build in the last few minutes. So as I was saying, the construction is inductive. And what I need to do is to take care, let's say I forget about the base step, let me take care about the inductive step. So at the inductive step, you need to imagine that you have built the manifold, capital M tilde j minus 1 together with an action of capital gamma j minus 1. What happens is that you build a new manifold, okay, that we already dealt with in the previous, in the last few minutes. Now I need to tell you how the new generator, little gamma j, the generator of the group capital gamma j, is acting on the part of the manifold that you added at the top of the guy. Okay? And I stipulate that the action of little gamma j on the new copy that I add on the top of the manifold of S3 cross D4 is gonna look as follows. It's gonna be by Hopf rotation with angle 2 pi over that product, K1, Kj, on the S3 factor. Let me notice that that product is indeed the order of gamma j. Okay? So it's rotating with angle 2 pi over the order on the S3 factor. Okay? However, it is rotating with a different speed and a different angle on the D4 factor. So now I'm viewing D4 in radial coordinates. So I'm viewing it as a warp, let's say a warp product of an interval together with a free sphere. And the action is moving only the free sphere, and it's keeping the radial coordinate fixed. And on the free sphere, this is going to rotate with a different angle. The angle is 2 pi over kappa j. Okay? And if you undo the algebra, you can easily check that this is going to be in the terminology that I introduced in the previous slide. This is going to be a mixed Hopf rotation. And in particular, it's a discrete subaction of the action that I denoted by, of the circle action that I denoted by 1 comma k1 dot dot kj minus 1. Okay, you just need to check that the ratio between the speeds of the two rotations is that guy. Okay, so this is a mixed action. It's rotating on both components. Okay, however, what happens? Let's see what happens if you look at the action of that guy once you take the kj power. Okay, once you take the kj power, the rotational component of the 4 disk is going to disappear, because that's exactly the order of the rotation of that guy. So once you take the kj power, the rotational component of the 4 disk factor is going to disappear, and you're going to be left with a pure rotation on the S3 factor. Okay, this, because of the algebraic structure of the problem, this is nothing but the action of little gamma j minus 1. However, the action of little gamma j minus 1 was already defined at the earlier steps of inductive construction. So there is a consistency check to make. Okay, and you need to recall that by the way the inductive construction works, what's going to happen is that on the end of the manifold that you're sticking in the inductive construction, so on the end of tilde capital M j minus 1, the action of that guy, little gamma j minus 1, is going to be it's going to look like a different action, because the way the induction works is that the action of little gamma j minus 1 is going to be an action of that kind on the end of the manifold that is sticking. And so there is a kind of incompatibility. This incompatibility is fixable. However, this is telling you that the diffeomorphism that you need to use in order to glue the old guys into the holes that you cut onto the new part that you put on the top of the old guys, they must be non-trivial. They cannot be the identity. And indeed, they must be so non-trivial that they conjugate the two actions. So the diffeomorphism, in order for the construction to make sense, the diffeomorphism that you need to glue the old guys into the new guy must conjugate an action which is mixed. It rotates on both components, with an action which is not mixed. It is pure on only on the S3 factor. Okay? Any questions? Okay. If not, let me make a brief recap and focus on the main challenge that we need to face for the geometric construction. So as I was saying, what happens is that when you go along the inductive constructions, imagine that you are at the J step, so you are left with the copies with how many copies you wish of the manifolds that you build at the J-1 step of the inductive construction. Those manifolds a priori they are not going to be diffeomorphic to something reasonable that you understand. However, you understand that the ends of these manifolds are going to be diffeomorphic to an annulus into S3 cross R4, which you can view as S3 cross the cone over S3 sphere. And moreover, the action of the group capital gamma J-1 on the end of that guy is going to be by mixed rotation on both components. Okay? Now, when you stick a new copy of S3 cross D4 on the top of these guys, and you create the holes, what happens is that by the way I define the action of the new generator, the action of the new generator on the lower ends of this new guy that you add is going to look in that chart, is going to look like a pure rotation. Okay, just a pure rotation on the S3 cross factor. Okay, and the main technical challenge that you need to face is that basically what you need to do is you need to twist the ends of the manifolds that you build at the earlier step of inductive construction in order for the rotation, which is looks mixed at the bottom, let's say, you would like to twist the ends in order to make that rotation look like a pure rotation on the S3 factor while you move up. Okay? Okay. So before getting into the details of this gluing step, let me make a brief parenthesis, just discussing in a very broad sense gluing operations with where you care about the lower Ricci curvature bound or a positive Ricci curvature lower bound. So first remark that I would like to point out is that so we need to face a gluing challenge, let's say, and gluing challenges they can be highly non-trivial when you care about lower curvature bounds, and they can be highly non-trivial even if you only care about scalar curvature lower bounds. And the statement that I want to make is the following. So Itching in 74 proved that there exist exotic spheres. Okay, so manifolds homeomorphic to the standard sphere, but not diffeomorphic to the standard sphere, that we can be obtained by gluing to standard disks along the boundary with the diffeomorphism, which is not isotopic to the identity. And the obvious observation is that each copy of the two disks can come with a metric with positive Ricci, and if you care about it, it can also come with a metric with positive Ricci and convex boundary. However, each in statement tells you that there are such exotic spheres that can be obtained with this construction that do not admit any metric with positive scalar curvature, and a fortiori there cannot admit any metric with positive Ricci curvature. So the meaning, the idea is that you can start with two pieces which have positive both have positive Ricci curvature, and you wonder whether you can glue them together in order to get something with positive Ricci curvature. The answer is that in general you cannot do that. Okay. Now, on the other hand, there is an extremely developed theory of gluing with positive. There is no general theory, but there are several examples scattered through the literature of successful gluing constructions for manifolds with positive Ricci curvature. The first one, to the best of my knowledge, is the work of Shah and Yang in the 90s, who were able to endow connected sums of an arbitrary number of product of two spheres with a metric of positive Ricci curvature. Okay, that was a gluing construction. Comparing with what happens in the statement due to Ricci, Wright in 1997 was able to endow any exotic sphere with a metric with positive Ricci curvature. Let me also briefly mention work of Perelman and Ngui in the 90s, still relating to gluing, successful gluing with the positive Ricci curvature. Okay, so now let's discuss how the gluing happens in our example. So what you should keep in mind is that the gluing is not going to happen straight away. In order to make this gluing work, we are going to need to construct a neck which is going to be the neck where the twisting that I was alluding to in the previous slide happens. Okay, so this is a picture of what happens at the bottom of the neck. So those are, you should think of them about as being the radial slices of the neck. Okay, the radial slices are going to be all diffeomorphic to S3 cross S3. Okay, and what happens is that at the bottom of the neck, the action is rotating on both components. So this is a mixed action, but with whatever speeds on the two components. This is the picture of the manifold at the scale comparable to a little r j-1, one of the scales that I introduced in the previous in one of the previous slides. What needs to happen while you move along the neck is that the action is going to twist, and when you are at the end of the neck, the action needs to be pure rotation on the S3 cross factor. Okay. And I'm going to discuss this twisting of the cross sections in two steps. The first step is going to be a non-equivariant version where we don't care about the action, but this is going to be helpful in order to get the end picture in the case where we care about the isometric action. How much time do I have? Okay, great. Okay, so let me make first the comment, which is the comment giving a meaning to the statement that I'm going to discuss in a second. The comment is the following. Let's start at the group of diffeomorphisms of the three-sphere cross the sphere. And in order to make it non-trivial, to make the statement non-trivial, let me also just focus on those diffeomorphisms which are orientation preserving. Okay? Craig in 79 proved that such a group of diffeomorphisms is not path connected. Okay? And this is that statement which is going to give a non-trivial meaning to the next theorem. So the non-equivariant version of the twisting of the cross sections that we are going to need in a minute is the following. So let's start from the standard round metric on the product of two free spheres, where by round I mean that you're going to take just the sum of the round metric on the first free sphere with the round metric on the second free sphere. Let's fix whatever diffeomorphism you want. Let's say that it is orientation preserving in the diffeomorphism group of the product of the two free spheres. Then the statement is the following. You can find the smooth family of Riemannian metrics, GT, parameterized on 0, 1, such that G0 is the standard metric you started with. Okay, the Ricci curvature is strictly positive for all those metrics for any time. And what happens at the end of this construction is that G1 is going to be the pullback of the standard metric with respect to the diffeomorphism that we fixed. Okay? Let me make the observation that if the diffeomorphism phi is isotopic to the identity, this construction would be trivial. Okay? You could just fix a family of diffeomorphism interpolating between the identity and the guy that you fixed at the end. And you could take as a family of metrics the pullbacks with respect to the interpolating diffeomorphism phi of the standard metric you started with. So what makes this statement non-trivial is the statement that I mentioned at the top of the slide, that the diffeomorphism group of S3 cross S3 is not path connected. So a priori, there is no reason why something like this should work. Okay? Next, let me discuss the tool that we need in order to twist the cross sections, which is you should think of it as an equivariant version of the statement in the previous slide. So the theorem is the following. Let's fix again the standard product of two round matrix on S3 cross S3, and let's fix any integer. Then what happens is the following. You can find the diff from the manifold into the manifold, and a smooth family of Riemannian matrix GT as before, with the following three properties. So first, we need these sections to have positive Ricci curvature, strictly positive Ricci curvature for any time. Then I stipulate that the 1K circle action needs to be isometric for all such metrics. Okay, for any time, I want the OPF mixed rotational action with speeds 1 and k to be isometric for all those metrics. And as before, we stipulate that the end metric is going to be the pullback of the standard round metric with respect to a diffeomorphism. Now the diffeomorphism needs to have the property that it conjugates the 1K action, the 1K mixed action on both components with an action just rotating on the S3 factor. Okay, so this looks familiar because those are exactly the kind of diffeomorphism that we need in order for the diffeomorphic construction to work. Okay, very well. And let me also make the comment. I think it's instructive and much less technical to do an analogous construction for a family of flat Riemannian matrix on a two torus. So the statement is the following. The only modification that you need for the statement, besides the obvious one, is that you would like to build a family of metrics on the two torus which are all flat. Okay, they are not going to be standard, but you stipulate that they all need to be flat. And basically, this statement is let's say, roughly speaking, the Ricci positive version of that statement that you can get for flat Riemannian matrix on the two torus. Okay, any question on the statement? If not, sure. Sorry. Say it again. I didn't get it. You mean the free? Okay. So the free plays a role because of the preliminaries on the actions. Let's come back. I can tell you. Okay, without coming back to the previous slide. So we need the S3 because on the S3 you can find. There are two, let's say, competing factors. So you would like the manifold to have a reasonable metric with positive Ricci curvature. Okay. Second restriction, you would like to get a circle action which is free. Okay. And if you think, for instance, to the most obvious modification, which is let's say that we try with S2 instead of S3, then on S2 there is no free circle action. Okay. Higher would be worse because the goal was to build the lower possible dimensional counterexample. Okay, and like you can go higher, you can build such examples like at the algebraic level, they would work with S7, I think. And basically for that part of the construction, you need a sphere and you need it to admit a free circle action. Okay, and there are such spheres. Okay, any other questions? Okay, my last goal before getting to the open questions is to briefly discuss how to build the neck after you have at disposal the family of cross sections twisting as we have after this statement. So this statement you should think about it as the answer to the question about how to twist the cross sections in the neck that was displayed in one of the previous slides. Now our goal it's not enough to get cross sections with positive Ricci curvature. You like the whole neck to admit a metric with non-negative Ricci curvature. And the main idea in order to build such a neck is to borrow a beautiful old idea from a null paper of Moser in 1965. So the first reduction that you make is that from the statement of the previous slide, you reduce to the case where the volume form, not only the volume, but all the volume form of the family of metrics is constant with respect to time. Okay, and this is a very general statement, and the idea for the proof goes back to the paper of Moser that I mentioned. Once you are in such a place, then you can basically look for a metric on the neck which has the form of a generalized work product, where so the standard work product would be to put a fixed metric there and put a working function there. The idea now is that once you have made such a reduction, you can try for a generalized work product where this metric on the section is changing, and you put an additional factor in front of the metric on the cross section in order to help you. And this factor is gonna look approximately like the factor that you would place in there when you try to construct the com metric, let's say. And this is an idea which is basically an equivariant version of an idea that Caldini and Neighbor used in another construction a few years back. Let me make the comment that if it was the case that GT is constant with respect to T, which is not the case in our construction, then one could just take the com metric and choose f of r equal to r in that construction, and we would get a metric with non-negative Ricci curvature, which would play the role of the gluing neck that we need in the diffeomorphic construction that we discussed a few minutes back. And the idea is that if you allow the cross-section metrics to change very, very slowly, and the factor is going to help you in order to get still a metric with non-negative Ricci curvature on this gluing neck. So as soon as you're able to build a family of cross-sections which are twisting the action and they have uniformly positive Ricci curvature, getting a neck with the non-negative Ricci curvature becomes more of a technical thing. Okay, and in the last couple of minutes, let me discuss a couple of open questions related to Milnor's conjecture. So first, there is the obvious open question about what happens in the remaining dimensions. So we now have a family of counterexamples in dimension 7. You can trivially build out of it a family of counterexamples in any dimension greater or equal than 7. The conjecture is true in dimension lower or equal than 3. What happens in dimension 4, 5, and 6? To the best of my knowledge, the Milnor conjecture remains open even in the case where you strengthen the assumption that the Ricci curvature is non-negative to the much stronger assumption that the Ricci curvature is identically vanishing. Then, coming back to one of the previous slides, so I made the observation that Lee and Anderson independently proved that the Milnor conjecture actually is something much stronger than the Milnor conjecture. Finiteness of the fundamental group is true when the universe, when the manifold has Euclidean volume growth, so the maximal possible volume growth, and a much weaker assumption would be the assumption that the universal cover of the manifold has Euclidean volume growth, in which case the Milnor conjecture is still open to the best of my knowledge. And in the end, last question that I would like to point out is a characterization question about the possible discrete groups that can arise as a fundamental group of a manifold with non-negative Ricci curvature. Okay, there is a pretty good understanding of finely generated subgroups of fundamental groups of manifolds with non-negative Ricci curvature, but there is not yet a full complete characterization of possible fundamental groups. Okay, and this is all I wanted to say, so I thank you for your attention.
For your talk, are there questions?
Okay, so if I understood correctly, you can make these necks as long as you want somehow. Right. So that means that the volume growth can be as close to linear as you want.
Like the necks, you can build them as long as you want, but there is a step which I put under the rack, which is the gluing step where you're gluing to let's say KJ copies of the old guys.
Yes.
In that step, you need the manifold, you need the core that you add, you need it to look like, in the Gromov-Hausdorff sense, you need it to look like R4, flat R4, cross a free sphere. Okay, and then in that step, you are kind of growing with the volume growth, because if you just stare at the R4 cross S3, this is going to have volume growth, which is R to the 4th. Okay, so what happens is that you have something which looks like that, and then you want to shrink it down to something which looks like linear, and then the strange twisting happens, and then the manifold needs to grow again until it looks like R4 again. So it might seem like I think that if one is not careful with the construction that we wrote down, one would get something which with growth like maybe R to the 4th plus epsilon. But maybe if one is more careful, then it's possible that one might get very, very close to linear and even very, very close to maximal.
Okay, thanks.
Yeah.
I had sort of this very same question. So I ask you something that's very linked with that, but you said that you have this sort of range of volume growths, right?
Yeah.
From linear to R4.
Yeah.
But it keeps on ranging from linear to,
Yeah.
okay.
Yeah.
Okay, so as long as you go to infinity, it ranges between these two two scales. And is there, if I understood correctly, a sequence of radii such that the growth is linear?
I'm not completely sure. I'm not completely sure. The way the construction is written, I'm not sure there is one where the growth is exactly linear. Maybe you can modify it in order to achieve such a additional property, but I'm not completely sure. Like the picture is cleaner if you stare at the blowdowns of the manifold. If you stare at the blowdowns of the manifold, you're gonna get some blowdowns which are 4-dimensional. So the manifold is, let's look at the universal cover. The universal cover is 7-dimensional. You are gonna get some blowdowns which are 4-dimensional. So for instance, you get R4 as a possible blowdown, but you also get the half line as a possible blowdown. And from that perspective, the picture is cleaner because you get something which is oscillating between a half line. Basically, the picture you should have is that in the family of blowdowns, you get R4, then R4 is shrinking, it becomes a half line, and then it opens up again, and it becomes R4 again. Okay, so at the level of the dimensions of the blowdowns, the dimension is oscillating between 4 and 1, let's say, even to it jumps. The computation of the volume growth is a bit trickier because you have the growth coming from the previous scales, which is accumulating on the top, and then it's kind of harder to compute the exact volume growth. But it's possible that you can. It's still possible that you can arrange all the possible growth between the linear, which is the one excluded by Sormani, and the maximal, in which case I'm pretty sure our construction cannot get such a volume growth.
Okay, just to ensure my question was clear, I was meaning that there is a sequence of radii, okay, such that the balls of radius Ri over Ri goes to a constant.
Yeah, I got the question.
Okay, so this is okay.
It's not clear.
Okay.
It's a pleasure to have now Chiara from Padua. She's going to speak about non-normal conformal matrix on R4 with sign changing Q-curvature. Please start.
Thank you. And thank you, Alessandra, Luca, and Mattia for the invitation. It's a real pleasure to be here. Today I will speak about some results concerning nonlinear partial differential equations related to curvature invariance in conformal geometry. A model of such kind of differential equation is the prescribed Gaussian curvature equation, or analogously the prescribed Q-curvature equation under conformal change of matrix. Okay, in what follows, I will introduce briefly the main notions and about the geometric quantities arising in our problem, and then I will introduce my results. So, if there are any questions or there is something which is not clear, please stop me. So, okay, but let me briefly sketch the outline of this talk. I will speak about two problems. One is related to the problem of prescribing Gaussian curvature in the plane, and the other one is concerns the very related problem of prescribing Q-curvature. Okay. So, first of all, I will introduce what I mean by prescribed curvature problem, first dealing with the two-dimensional case, and then, after introducing the notion of Q-curvature and of Panet's operator, I will introduce the problem of prescribing Q-curvature. So in the first case, I will study this problem. This is the prescribed Gaussian curvature equation in the plane under this assumption on the total Gaussian curvature. And in this case, I'm interested in studying extents and compactness of solution to this problem. And in the second part of the talk, I will study this problem, which is the problem of prescribing Q-curvature in R4, in the 4-dimensional Euclidean space, under these assumptions, this assumption on the total Q-curvature. Okay, notice that both the problems we are dealing with have this kind of prescribed curvature, which is 1 minus the norm of x to the power p, where p is a real positive value. And the main point of this talk is to understand how this particular prescribed curvature influences extents and non-extents of solution to our problem. Finally, I will briefly sketch some open problems, but okay. First of all, I would like to talk about some basic notions of conformal geometry, which certainly most of you already know, but only just to give a global picture of the theory for people who have never seen it. So let us start with the two-dimensional case, and then we will see the corresponding problem in higher dimensions. So we consider a Riemannian manifold, a two-dimensional Riemannian manifold M, endowed with a metric G, and with the Gaussian curvature Kg. We are interested in the behavior of the Gaussian curvature under conformal change of metrics. So we consider a conformal metric to G, that is, there exists a function U belonging to C infinity, such that Gu can be written in this form, the exponential to the power 2U times G. And we will denote by Kgu the Gaussian curvature of the Riemannian matrix M endowed with the metric Gu. Using the analysis sign convention, so that the Laplace operator now is, for me, negative definite, we obtain that the Gaussian curvature equation reads as follows, is this one. And in this case, the delta G is the Laplace-Beltrami operator, which is a conformally covariant operator because it satisfies, it transforms according to this rule for every phi belonging to C infinity. And what is interesting is that the Gaussian curvature equation relates the Gaussian curvature Kg with respect to the metric G to the Gaussian curvature with respect to the metric Gu. Using the Gauss equation, we can integrate in the Gauss equation in the case when our manifold is closed, namely compact and without boundary and orientable, we can obtain this equality, which tells us that the Gaussian curvature equation, the total Gaussian curvature equation, is conformal under is invariant under conformal change of metrics. Okay, so we can say also that the total Gaussian curvature is a global conformal invariant. Finally, the Gaussian curvature equation gives us information about the topology of the manifold, because we can use the Gauss-Bonnet theorem and obtain that the total Gaussian curvature is equal to 2 pi the Euler characteristic of M. Okay, these two conformal properties will be very useful in our results. Okay, a very classical problem in conformal geometry is the problem of prescribing Gaussian curvature. That is, if we have a smooth function K on a manifold M endowed with a metric G, finding whether there exists a conformal metric Gu having K as its Gaussian curvature. So these problems corresponds to find the solution to this equation, which is the so-called prescribed Gaussian curvature equation. And so if U solves this one, then the metric Gu, defined in this way, has Gaussian curvature equal to Kg. Okay, let me briefly recall some literature about this problem. In the case when our manifold M is the two-sphere endowed with a standard round metric, this is the so-called Nirenberg problem. It has been raised by Nirenberg in the 70s, and it has been widely studied by Kazan-Warner, Aubin, Chang and Yang, and many others. And I want only to recall the work of Kazan and Warner, because they gave some necessary and sufficient condition to a given smooth manifold, a smooth function, to be the Gaussian curvature of a compact two manifold. And what is important is that the result depends on the topology of the manifold, the sign of the Euler characteristic of the manifold. Okay, on the other hand, if we consider the Euclidean plane endowed with the standard Euclidean metric, that is the flat metric, it's obvious that the Gaussian curvature is equal to 0, and the Laplace-Beltrami operator is the classical Laplace operator. So the equation is this one. The prescribed Gaussian curvature equation becomes this one. This PD has been intensively studied during last decades, and just to recall the work of Liouville, the study of this equation start with the work of Liouville. We studied the case when K is equal to 1, And then, for example, in the case when k is a positive constant, Chen and Li prove that all solutions to this equation are symmetric with respect to some point in R2. They use the method of moving planes, and all solutions are spherical. Okay, but we will say later what I mean by spherical. Okay, we are ready to introduce our first problem. The results we deal with in the first part of this talk concern this problem. So we have the prescribed Gaussian curvature equation in R2 and this condition on the total Gaussian curvature. So external result with and non-external result will depend on the value of P and on the value of the total Gaussian curvature. Using some positive type identity and some results about the behavior at infinity of our solutions, we are able to prove the following non-external result. In the case when lambda is less than lambda star p, where lambda star p is this value, or lambda is greater or equal than 4 pi. In this case, as I said, our problem has no solution. Moreover, also when p is greater or equal than 2, we have no solution for every value of lambda. On the other hand, we're able to prove the following external result, because when p is between 0 and 2, and lambda is between these two real values, we are able to prove existence of a radially symmetric solution to our problem, and the solution has this asymptotic behavior when the norm of x is sufficiently big. To prove this result, we use a result by Chang and Chen, which we will see later, and using this result, we are able to prove existence of at least one radially symmetric solution to a slightly perturbed problem. Then, using a blow-up argument, we are able to find solution to our problem. But okay, the proof of this result is quite technical, so it's not so interesting. I will skip it. What I want to observe is that from the two previous results do not cover the case when lambda is equal to lambda star p. We will study this case from the point of view of compactness. So concerning compactness, a very famous and seminal paper by Brazis and Merle studies compactness of solutions to this equation in a two-dimensional manifold, in two-dimensional domain. And in particular, if we have a sequence of solutions to this equation in omega, and we assume that the volumes are uniformly bounded in K, and also that the curvatures are positive, and their L-infinity norm is uniformly bounded in K, we are able to say, Brazis and Merle are able to say that either we have compactness, so we can you can extract a subsequence converging in C1 log to a certain function U bar solution to the limiting problem, or we have a blow-up, namely there exists a blow-up set, a finite blow-up set of all points in omega, such that for every arbitrary small ball centered in this point, there is a sufficient amount of curvature, which must be at least 2 pi. 2 pi in this case is half of the total curvature of the sphere. Okay, what happens is that away from this blob set, our function goes to minus infinity, and the curvatures concentrates all in the points of the previous blob set. Okay, in our case, we use this result to prove our results, but in our case, we have a different scenario, because differently from the result of Brazis and Merle, we assume to have a fixed prescribed curvature, and we assume that the total Gaussian curvature change. Namely, we assume to have a sequence of solution to our problem, okay, and such that the values of the total Gaussian curvature belongs to this interval. And we assume that lambda k goes to a certain lambda bar belonging to this interval. What we're able to prove is that when the sequence lambda k is away from 4 pi, there is compactness. So there exists a subsequence which converges locally uniformly to a solution to our problem, and such that the total curvature of the solution U bar is equal to the value of the limit lambda bar. Okay, what is interesting is that using this result, if we assume to have a sequence of lambda k converging to lambda star p, we are able to prove excellence of solution to our problem in the case when lambda is equal to lambda star p, which, as I said, is not covered by the previous result. And moreover, solutions are bounded from above in this way, when the norm of x is sufficiently big. Okay. In order to prove this result, we use a blow-up argument. That is, we use the previous result by Bredes and Merle, and a further result by Lee and Shafrir about quantization of the total curvature. And we are able to obtain some elliptic estimates, uniform elliptic estimates. And so we are able to prove that there exists a subsequence local, which converges locally uniformly. The difficulty now is to prove that our solution has total curvature, Gaussian curvature, equal to the value lambda bar, because a priori we could have loss of negative curvature at infinity, but we don't have this case because we can use an argument based on the Kelvin transform, and so we are able to conclude. On the other hand, if we consider a solution of lambda k which goes to 4 pi, we prove that our solutions blow up spherically at the origin. So consider a sequence of solution to our problem such that the values of lambda k converge to 4 pi when k goes to plus infinity. We are able to prove the sequence of curvatures converge weakly in the sense of measure to 4 pi, the Dirac delta centered at the origin. And when I say spherically, I mean that there exists a suitable rescaling of our function uk, such that the obtained function, this one, converges to a spherical solution of our problem. It's in one lock. I will say later what I mean by spherical, okay? The proof of this result is based on the fact that we can have only two possibilities from the previous result about from these two results. We can have or loss of compactness when lambda k goes to 4 pi, or loss of negative curvature at infinity. The case of loss of negative curvature at infinity is ruled out because we cannot have solution when lambda is greater or equal than 4 pi. So we have loss of compactness. And in particular, using some results which extends the previous ones by Bredes and Merle and Lee Shafrir, we can conclude. Okay, so now I would like to introduce the Q-curvature and the Panetz operator. Analogously to the concept of Gaussian curvature on a surface, we can introduce an equivalent notion of curvature on a 4-dimensional manifold and define an equivalent problem in higher dimension. So, analogously to the Gaussian curvature, we can define the Q-curvature, which is related to conformal operator, and whose integral gives information about the topology of the manifold. Okay, so let us take a manifold M endowed with a metric G, a 4-dimensional Riemannian manifold, and we can define the Q-curvature and the Panetz operator in the following way. Okay, here Rg is the scalar curvature, Ricci is the Ricci tensor, delta G is the Laplace Beltrami operator, and D is the classical differential acting on function. This definition has been introduced by Branson, Wersted, and Panetz, and then they have been generalized to higher order Q-curvature and Panetz operator on a general 2m-dimensional Riemannian manifold. What is interesting is that we don't have, when 2m is greater than 4, we don't have an explicit formula for this, for the Q-curvature and the Panetz operator of order 2m. But Graham, Jen, and Marston and Sparkling, from which the alternative name, GJMS operator, gave a formal definition of the Panetz operator and of the Q-curvature. Okay, roughly speaking, we can say that the Panetz operator is a sort of higher order Laplace Beltrami operator, while the Q-curvature is the higher order counterpart of the Gaussian curvature. Okay, similarly to the Gaussian curvature, the Q-curvature and the Panizza operator are related by a generalized version of the Gauss identity. Indeed, they satisfy this relation, which tell us also information on how behaves the Q-curvature under conformal change of metrics. Moreover, similarly to the Laplace-Beltrami operator, we have that the Panizza operator is conformally covariant, that is, it transforms according to this rule for every phi belonging to infinity. And moreover, using the Gauss identity, in the case when our manifold is closed, and integrating it, we obtain that the total Q-curvature is a global conformal invariant. Okay, as before for the Gaussian curvature, using the Gauss-Bonnet theorem, in the case when our manifold is locally conformally flat, otherwise we have here another term, okay, but assume to have a locally conformally flat manifold. And so in this case, we can say that the total Q-curvature is equal to the factorial of 2m minus 1 times the volume of the 2m sphere times 1/2 the Euler Poincare characteristic of M. So the covariant properties of the Panizza operator and the Q-curvature are quite interesting. Okay, analogously to the prescribed Gaussian curvature, to prescribing Gaussian curvature, we can prescribe the Q-curvature, and so given a smooth function K on our manifold, we can ask if there exists a conformal metric having Q-curvature equal to K. Okay, so in this case, similarly to before, our problem consists in finding solution to this equation, which is the so-called prescribed Q-curvature equation. And so if U solves this equation, the conformal metric GU has Q-curvature equal to K. Okay, briefly, some literature about the prescribing Q-curvature problem. In the case when our function K is constant, Chang and Yang gave a positive answer to this question, and they proved that in the case we have a 4-dimensional manifold, and assuming that the total Q-curvature is less than the total curvature of the 4-dimensional sphere, and also assuming that the Panizza operator is non-negative and its kernel only consists of constant function, they prove existence of a conformal metric. This assumption was later weakened by Gursky, because he proved that a necessary condition to have that the kernel is made only of positive constant function, sorry, is that we have to assume that the total Q-curvature is positive, and requiring that our manifold is of positive Yamabe type. By positive Yamabe type, I mean that there exists a conformal metric of constant positive scalar curvature. Okay, this result was then generalized by Brendel in higher dimension using a flow approach, always assuming this subcritical condition, which precisely rule out the case when our manifold is conformal to the standard round sphere. Okay. Later, Daniele and Malchiodi studied this problem, extended the result by Chang and Yang, assuming always to have this condition on the kernel, and but assuming only this condition on the total Q-curvature. Namely, the total Q-curvature must be different from an integer multiple of 16p squared. And finally, before I spoke about the Nirenberg problem, Malchiodi and Struve studied the corresponding Nirenberg problem on the standard S4. And the results, they use a geometric flow to prove that this geometric flow gives rise to extents of solutions when the prescribed curvature is constant, or in other case, gives rise to blow up of the matrix near some point of the S4. Okay. In the case when we consider the 2m dimensional Euclidean space endowed with the standard Euclidean metric, it's easy to verify that the Panet's operator is this one, so is minus the Laplacian to the power m, and the Q-curvature is identically equal to 0. So the prescribed Q-curvature equation becomes this one. And in particular, the constant curvature case for this equation has been intensively studied due to its geometric meaning. In particular, if we assume to have k equal to the factorial of 2m minus 1, and we require that the solution have finite volume, a family solution to this equation is the following one. So for every lambda greater than 0 and for every point in R2m. And this solution has this volume. The volume of this solution is equal to the volume of the 2m sphere. These kind of solutions are called spherical solution because they arise under as the pullback under the stereographic projection of round metrics on the standard 2m sphere. When I mean round metric, I mean that it's a metric which is conformally diffeomorphic to the standard metric on the 2m sphere. And just to tell that choosing this particular constant Q-curvature is not restrictive. We can also study this problem with another positive constant. We take the factorial of 2m minus 1 because this is the Q-curvature of the 2m sphere. And for example, Cheng and Yang proved that round metrics are the only metrics having Q-curvature equal to the factorial of 2m minus 1. Okay, this equation has been intensively studied, as I said. In the case when we are in the plane, so in the case when m is equal to 1, Chen and Li studied this equation and proved that, as I said before, that all solutions are symmetric with respect to some point, and all solutions are spherical in this sense. They assume this form. Okay. In the case when m is greater or equal than 2, the situation is a little different because we have non-spherical solution. Chang and Chen proved that for every m greater or equal than 2 and for every volume between 0 and the volume of the sphere, there exists at least one non-spherical solution to our problem. And then other authors studied and classified all the solutions to this problem when m is equal to 2 and m is greater or equal than 2. Okay, so I would like now to introduce my second problem. So assume to have P, a positive fixed real value. We want to study the prescribed Q-curvature equation in R4, and under the assumption that the total Q-curvature is finite. Geometrically, this means that if U is a solution to this problem, the conformal metric GU, conformal to the Euclidean metric, has Q-curvature equal to 1 minus the norm of x to the power p, and the total Q-curvature equal to lambda. Now the difficulty lies in having this particular Q-curvature because it changes sign and it is unbounded. So the classical techniques used to prove such kind of results do not hold now, and so there are some difficulties. And so, okay, in what follows, I will always assume that this quantity is in L1, and if U is a solution to our problem, I define the V in the following way. Okay, this is this integral. It's this integral. In my study, I'm interested in studying normal and non-normal solution. Roughly speaking, normal solution can be written in integral form, but more precisely, a solution to our problem is called normal if there exists a real constant C such that U solves this integral equation. Okay. All other solutions are called non-normal. Okay, but let us see now what we already know about the previous problem, this one, and what we are going to prove now. Okay, recently either concerning normal solutions, okay, recently either Martinazzi proved some extents and non-extent results. In particular, among other things, they proved that non-normal solution normal solutions, sorry, do exist if and only if P is between 0 and 4 and lambda is between these two values. Such solution has the following asymptotic behavior when the norm of x is big. Okay, motivated by this result, we want to study properties of more general solution to our problem, not necessarily normal. And the first thing that I prove is extents of non-normal solutions. Then I prove a general classification result. And finally, I geometrically characterize solutions in terms of the behavior at infinity of the scalar curvature of the associated conformal metric GU. Okay. Okay, as I said, in this case, normal solution exists only when P is between 0 and 4. Although for P greater or equal than 4, non-normal solution not exist, normal solution do not exist, we are able to prove that non-normal solution do exist. To do that, we define the following set of polynomial in R4, having degree equal to 2, and whose limit when the norm of x goes to plus infinity is equal to minus infinity. So this set of polynomial. And using a result by Chang and Chen, we are able to extend the previous result, which I mentioned above. And okay, the extra result we prove is the following. For every polynomial which satisfies these conditions, and for every value of the total Q-curvature between 0 and 16p square, there exists at least one solution to our problem, which has this form, W plus P, and such that W behaves logarithmically at infinity. Okay. As I said, we use a result by Chang and Chen, which can be found in this, I don't know if you can see in this work. Okay, they assume to have this equation in even dimensions. And they assume that the curvature kx, the function kx, is positive somewhere, and there exists a certain s greater than 0, such that this condition at infinity holds. Okay, in this under this assumption, there exists at least one solution to our problem. Okay, assume to have a certain fixed p belonging to the previous set of polynomials and a certain lambda between 0 and 16p square. We can fix kx in the following way: 1 minus the norm of x to the power p, the exponential to the power 4 capital P. It's easy to verify that this function satisfies the previous condition. It's positive somewhere and satisfies this. Okay, so we are able to find a solution to this equation with the total Q curvature equal to lambda. Now we are done because U equal to W plus P is a desired solution to our problem. In order to conclude, we have to study the asymptotic behavior of W. So in order to study this, we have to see more in detail how we construct W. So W is equal to this sum, where W0 is a classical spherical solution, this one. W tilde is defined as W bar plus C, where W bar minimizes a certain functional, and C is such that this integral is equal to 1 minus mu to the power times 4 pi. And we can see that W tilde satisfies this Euler-Lagrange equation. In particular, we see that this quantity is in L infinity. This one is in LQ for every Q greater or equal than 1 and less than plus infinity. So by elliptic estimates, we can say that W tilde is in C3 alpha, okay, for every alpha greater than 0 and less than 1. In particular, W tilde is continuous at the south pole, so we can write this equality, and evaluating it, we are done. Okay, and next, we are able to prove the following classification result, which tell us that every solution to our problem can be written as V, where V behaves logarithmically at infinity and is defined as before, and P is an upper bounded polynomial P of degree at most 2. Okay, and V and U, sorry, as this asymptotic behavior. Notice that P being upper bounded means that means that P has an even degree, but since P can only have degree at most 2, this means that P could only be a polynomial of degree 2 bounded from above or to be constant. Okay, so we can rephrase this theorem saying that all solution to our problem, if the solution to our problem is a non-normal, P is an upper bounded polynomial of degree 2, while if the solution is normal, the polynomial P is equal to a constant. Okay, in order to prove this result, we proceed by steps. So first of all, we have to prove some suitable upper and lower estimate for the function V. We have to overcome some difficulties due to the fact that in this case we have an unbounded and sign changing Q-curvature, so we have some difficulties with respect to previous works. And in particular, the lower estimate will be crucial to obtain a Liouville type theorem. And also in this case, in the lower estimate, we have this singular integral, which a priori can be also very big. And finally, we prove that our polynomial is upper bounded. And to do that, we use a result by Goring and the fact that we are able to prove that this quantity is bounded. This singular integral is bounded. Okay. The difficulties with respect to previous works are the following. If we would like to follow the approach by Lin, we study the case when the Q-curvature is constant, we must know the sign of the Laplacian of U, and then apply an Harmonic inequality. But in our case, we don't know which is the sign of the Laplacian of U. On the other hand, if we would like to follow the approach of Martinazzi, we have to know a better estimate for the function V, which now we don't have because there is this singular integral. And so, okay, we have some difficulties with respect to previous works. Okay, so as I said, we have to prove suitable upper and lower estimates for the function V. Okay, we prove that when the norm of x is greater or equal to 4, there exists a constant C such that the function B is bounded from above in the following way: the logarithm plus a constant. Okay, the proof of this result is quite easy because, okay, we have to decompose it's standard. We have to decompose the Euclidean space R4 in a suitable way, and then we have to estimate this integral in each of these sets. Okay, and then we have to put together. The only difficulty with respect to previous work is in having this particular prescribed Q-curvature. Okay, we are able also to prove a lower estimate. So for every epsilon greater than 0, there exists a radius R epsilon, such that for every x with norm of x greater or equal than R, V is bounded from below in the following way. As I said, now we have this singular integral, which is the problem. Okay. Okay, the previous lower estimate will be crucial to obtain this Liouville type theorem, and in particular assume to have that this quantity is in L1, the function V is in L1 lock, and also that the function A is biharmonic and bounded from above by U minus V. If this condition holds, the function H is a polynomial of degree at most 2. Okay. To prove this result, we use some elliptic estimates for H, which is a biharmonic function. And so we are able to say that all the third derivatives are bounded in this way. We use the fact that the norm of H is equal to minus H plus 2 times the positive part of H. And so we have to estimate this term and this one. Okay, to estimate this term, we use the Pizzetti formula, which is a sort of higher order mean value inequality. So the estimate for this term, it's okay. Then we have to estimate the other integral, and to do that we use the previous estimate for h, this one. Okay, we integrate, and okay, the first integral goes to 0 when the norm of r goes to plus infinity. It's easy to verify. What is more tricky is to verify that this one goes to 0. Okay, we use the previous estimate for the function v. Now we have to estimate the positive part of minus v. We are able to prove that the function ax is in L1, and so we are able also to estimate in a good way the immediate integral of the positive part of minus v with a constant, the logarithm of r plus a constant over r4. Okay, we have almost done because, okay, recall that in front of this integral we have a 2 times a constant over r3, and so we are done because this goes to 0, and we have proven that the third derivatives are identically 0. Okay, we have almost done because now we can use the previous theorem, this theorem, assume to have h equal to 1 minus v. Okay, you can see. We can evaluate the Laplacian of h. It's easy. It's equal to the Laplacian of u minus the Laplacian of v. So u is a solution. This is equal to 1 minus the norm of x to the power p, the exponential to the power for u, minus the same quantity. Okay, 1 minus the norm of x to the power p. We have defined v in a suitable way such that the Laplacian is equal to 1 minus the norm of x to the power p, the exponential to the power for u, so it's equal to 0. Okay, it satisfies this condition, is obvious. So h is a polynomial of degree at most 2. Okay, we have proven a partial classification result. Okay, so okay, we are here. We are able to prove that if u is a solution to our problem, u can be written as v plus p, where p is a polynomial of degree at most 2. Now we have to prove that p is upper bounded to conclude, and also to prove a better estimate for v, because in this it's useful to prove the asymptotic behavior for the function u. Okay, in order to prove that our polynomial is bounded from above, the first step is to estimate the term, the singular integral in the estimate of the function v. And to do that, we have, first of all, we have to split the integral. So we have the integral over the ball of radius 1 in x minus the ball of radius tau in x, plus the integral over the ball of radius tau in x of the quantity we have before. Okay, the first integral, it's easy, it's bounded. We have to estimate the other term. To do that, we use an order inequality, and we arrive to estimate this term. So in order to estimate this term, we use properties of the Green function and also some elliptic estimates. We are able to prove that there exists a certain tau greater than 0 and less than 1, such that this quantity is bounded. Okay, next step is to prove that the polynomial is upper bounded. Okay, assume by contradiction that the supremum of the polynomial is equal to plus infinity. We define a suitable function in this way. F of r is equal to the supremum of our polynomial over the boundary of the ball of radius r. Using an old result by Goring, we are able to prove that there exists a certain s greater than 0 such that the limit is equal to plus infinity. Moreover, using that our polynomial has degree at most 2, we can estimate the gradient of p in the following way when the norm of x is big. And so we know that u is equal to v plus p for V, we use the previous lower estimate. So we know that V is greater or equal than minus a constant, the logarithm of the norm of Y plus a constant, because we have proven that, that the term with capital A is bounded. And for the polynomial, we use its linearization, and we are able to prove that for every there exists a certain R0, such that for every R greater than R0, we can find a certain XR of norm equal to R, such that this quantity grows as R to the power S. And we are in the ball centered in XR of radius 1 over R. Okay, we are almost done, because we consider the total Q-curvature over the complement of the ball of radius 1. And we can estimate it, and we arrive to this integral. The integral from R0 to plus infinity of the exponential to the power 4rs over R3. This quantity is equal to plus infinity, so we have a contradiction. So because we assume that the total Q-curvature is finite. More in detail, that this quantity is in L1. Okay. Okay, we have to obtain a precise estimate for the function V. From the previous lower estimate for V, now we know that the modulus of A con X is lesser or equal than C. So we are done. Okay, we have this estimate. Using the previous upper estimate for V, we can obtain the desired estimate for the function U. Okay, when the norm of X is big. Okay, we are able also to obtain an estimate of the limit of the gradient of V when the norm of X is big. It's quite easy. We take the expression for V, we integrate it, we derivative it, and okay, we study its behavior when the norm of X goes to plus infinity. It's easy. We can consider the integral over R4 minus the ball of radius sigma centered in X. By dominated convergence, this one goes to 0, and the other integral, the integral over the ball of radius sigma centered in X, is quite small, okay, goes to 0. Okay, finally, as I said, we can geometrically characterize solutions in terms of the behavior at infinity of the scalar curvature of the associated conformal metric. So we are able to prove that when the solution is normal, the limit of the scalar curvature when norm of X goes to plus infinity is equal to 0. And when the solution is non-normal, the NIM-INF of the scalar curvature when the norm of X goes to plus infinity is equal to minus infinity. This result tells us that normal solutions have a quite different geometry compared to the geometry of non-normal solutions. And moreover, this tells us that the Q-curvature and the scalar curvatures are independent between them. To prove this result, we use the expression which relates the scalar curvatures, and we use, for example, this previous result of this limit, okay? And to conclude, as I said, we are able to prove that non-normal solutions do exist when lambda is greater than 0 and less than 16 p square. On the other hand, normal solutions do exist when we are between these two real values. Was 1 plus p over 4, 8p square. Lambda must be between these two values, 16p square. Here we have normal solutions when lambda is between 0 and 16p square. We have non-normal solutions. So it's open if there exist solutions having Q-curvature greater than this threshold. If we, in the literature, there is this work by Lin, which I mentioned before, he studied this equation. So he has constant Q-curvature equal to 6, and is able to prove that this problem has solutions only when the volume is between 0 and the volume of the standard force sphere. His approach is no longer applicable because we have this Q-curvature which change sign, and so it's not we cannot proceed in the same way. So it's open if there exists solution of total Q-curvature finite but greater than 16p square. On the other end, if we look for solution having total Q-curvature equal to plus infinity, we observe that radial solution must have finite total curvature. Also, this is similar to the case when k is constant. But when the solution is not radial, maybe we can have a solution with infinite total curvature. And finally, another question is to generalize the previous result to higher dimensions, so higher even dimensions, and for different assumption on the Q-curvature. So I've done. Thank you.
For the talk, question?
Yeah, I wanted to ask, when you apply the Poujave identity, do you need that exact or a special form of the coefficient 1 minus x to the p, or just the asymptotic set infinity?
I don't remember very well, but I think only the asymptotic behavior of solutions at infinity. But the Poisson type identity depends on these, originates by these our equation. So it depends on having this particular curvature, which is in signs.
Yes, I was wondering whether you could prove non-existence for a set of parameters as in your first theorems. So minus infinity to some lambda star, and then so whether you have for more general coefficients a structure of that type.
But we're talking about the 4-dimensional or 2-dimensional case?
Any.
Okay. I don't know. Maybe yes, I have to think better to it. Okay, thank you.
So I also have a question, maybe it's a bit far from what you did, but at the very beginning you mentioned that Brendel proved some result through flows.
Okay.
Which kind of flow? Do you have an idea what he did?
No, I don't have studied this work very well.
That's why I asked.
Yeah. Sorry.
It was clear, but
honestly,
it's
no.
different. It's very different.
I don't remember now.
So I will ask something maybe very basic, but like, so I never studied this kind of problems. And like, when you first see the definition, at least for me, of normal or non-normal solution, you're a bit like, this is a bit random, right? At least for me. So what's the meaning of, I mean, what's special about normal or non-normal solution, about normal solutions, let's say, like why that formula?
Okay. Okay. It's a convention. When you have a normal solution, it's everything. It's easier because you can use this quantity. Here you have a constant, so you don't have problems. Also, when you derive it, you evaluate the Laplacian, the Laplacian, you don't have problems. When you have here a polynomial, the situation changes.
No, yeah, I agree. But like, why log and not log? Like, I mean, what's special about that formula precisely?
Okay, because you want to define this, which if you evaluate its Laplacian, you obtain that solves our equation. And so you put it here. I don't know how can I explain better.
It solves the Laplacian equal to 0.
See, yeah.
Okay, so it's like
It's in a distributional sense.
Oh, okay, I see. Okay.
Now we have the last talk for today, and the title is Geometric Uniqueness for the Plateau problem. Plateau problem. Diciamo
Okay.
And let's try to be super supportive. It's the first talk. So let's start.
Okay. Yes. Okay. So thank you very much to Alessandra. Thank you very much to Luca and Mattia for the nice invitation. I'm very pleased to be here in Pisa. I'm very pleased to be here in the Centro di Ricerca De Giorgi. And that's actually very pleased also to be the character of this wonderful fourth season of the series of geometric analysis workshop in Pisa. And so I will present a joint work with Andrea Marchese, who is my PhD supervisor, Andrea Merlo and Simon Steinbrüchel. And mostly I will talk about well-posedness properties of minimizing surfaces. And I will talk about that mostly from a geometric measure theory point of view. So, okay. And I sketch here a quick outline of my talk, and that is almost divided. I mean, it is divided into three parts. The first one is just an introduction to what I will call the oriented Plateau problem. I will set up the notation, I will recall the main results, and I will, in an informal way, give you at the very beginning the result of our talk, of our seminar, I mean, of our paper. And the second part, I will need to recall some results in the theory of regularity, in the regularity theory for area minimizing integral currents. And I will recall some previous literature about the uniqueness of the solutions. And the third part, for all the time that I will have left, I will try to dig deeper into the main ideas of the proof of generic uniqueness for area minimizing integral currents and the generic multiplicity one. Okay, so as I sketch here, the first part in the introduction, the Plateau problem consists, we all know, in finding the surface of least area spanning a given contour. And the beauty of this problem is that really depending on the mathematical rigorous meaning that you give to the word surface, to the word area, and to the word spanning, you really are able to develop different formulations and different theories that are providing beautiful mathematics. So actually the Plateau problem can be considered not just as one problem, but really as a collection of problems, okay? So just to be on the a bit more rigorous than that, let me write what I will consider from now on, what is known as the oriented Plateau problem. Okay, so say, I hope that you can say that I give you gamma, which is an m-1 dimensional submanifold, which is oriented, so oriented submanifold, which is a boundary, of course, in calligraphic M, which is an m plus n dimensional Riemannian manifold. What we want to find is, so find sigma, which is going to be an m-dimensional oriented submanifold in M, such that sigma is area minimizing and spans the boundary. So the boundary of sigma is going to be gamma, okay? So this condition here has to be intended in the usual differential topology sense of taking the boundary. And for area minimizing, I mean that for all the competitors that are taking the boundary gamma, sigma is minimizing the volume, the m-dimensional volume, okay? So just to have the notation clear, let me remark it here, but to be sure. So maybe I should write it like this. Well, no problem, I write it here. So the dimension of the object we want to find the minimal area is going to be, from now on, m. The dimension of the boundary is going, of course, to be m-1. And the dimension of our ambient space is going to be m plus n. So you immediately realize that this n here is playing the role of the codimension of our surface in the ambient space. Okay, I will stick to this notation. Okay, so now you see this oriented Plateau problem, and the approach I want to take is the one of variation, of calculus of variation, the distribution in a sense approach. So we immediately see the variational nature of this problem. So what we want to find is to be able to apply Weierstrass theorem, so the direct method of the calculus of variation. And to be able to do that, you want, of course, this is trivial, enlarge the space of solutions. So you want to embed your space of oriented surfaces into a bigger space so that you can find compactness and try to solve the problem. So the thing is that we want a weak topology or such a weak notion of convergence to be able to get compactness. The problem is that if you want to do some things like that, you basically go into two problems. The first one is that you may have appearance of singularities. So think about paraboloids that are smooth, that are converging, and they converge to a cone. Then at the tip of the cone, you get a singularity. Another phenomenon that you need to take into account is that maybe you have two curves, something like this, two oriented curves, that somehow, in this way, they're oriented in the same way, they are coming across together. And then you want, in the limit, to be able to say that this curve oriented in this way is counted with a weight 2, a multiplicity 2. At the same time, if this curve here is oriented in the same way, you want in the limit to be able to allow for cancellations. Okay, these two phenomena may happen, and indeed, these are integer rectifiable currents. Okay, good. So integer rectifiable currents. So in a nutshell, integer rectifiable currents are really a countable union of pieces of C1 oriented submanifolds taken with integer multiplicity. Okay, so just to have everyone in the same page, let me recall what they are. So an integer rectifiable m-dimensional, because it is an object that comes with a dimension, integer rectifiable m-dimensional current is a linear and continuous functional on the space of smooth and compactly supported M forms. On the space of smooth, compactly supported M forms, for which there exist three sequences of objects, for which there exist three sequences. Let me call Si, Ki, and theta I, okay, where, I mean, such that these SIs are C1 oriented m-dimensional oriented m-dimensional submanifolds, I mean, submanifold, okay, embedded, but that's okay. KIs are just pairwise disjoint closed sets, so pairwise disjoint closed subsets of Si, and these theta i's are just natural numbers, okay, for which you have the following condition. You require that this infinite series from I equal 1 to plus infinity of the theta I times the m-dimensional volume of each closed set is finite, first. And second, you want your linear and continuous functional to act on forms in this way. You take t, the action of t on omega, which is a form, as the infinite series I equal to 1 to plus infinity, theta I integration over each ki of the form omega, okay? And this series is converging because of this condition here, okay? Great. Now, note, and this integral can be understood in the sense of Lebesgue, for example, okay? Good. So these objects come naturally with a definition of boundary and a definition of volume, okay? So let me just define it here. So we call the boundary of a current T just this action, T boundary of T on phi, is defined to be the action of T on the differential of phi, where phi is an m-1 smooth and compactly supported form. Okay. And then we have a notion of mass, which is a notion of area or volume. Let me call it mass, area of T, which is the following. So we define the mass of a current T as the supremum of the action of T over all forms which have norm, smaller or equal than 1. Okay. And in this particular case, what the mass of an integer rectifiable current is just the infinite series of theta I and the volume of each ki. Okay, infinite. Good. So some remarks. First remark is that these notions are really generalizing smooth surfaces, because if we take a smooth surface, then this action here is going to be just the action on form over the C1, say, oriented submanifold. The notion of boundary is going to be the definition of boundary is going to be enforced just by Stokes' theorem, and the notion of area is just going to be the volume of your C1 manifold. Okay, good. So the first remark is this one, that when we have a smooth oriented submanifold, we will denote with this funny notation, okay, just the action of the integer rectifiable current naturally induced to the smooth manifold. Okay, good. Second remark is that since you understand that there is a duality notion here that is playing the role, so we will naturally keep this space with the notion of weak star topology. So we will say that a current is converging in the sense of currents to another current if they're converging the weak star topology. And third remark, so weak star. And third remark is that, just a notation, that if T and the boundary of T are integer rectifiable currents, then we say that T is integral. Okay, good. So for those of you that are already familiar with the theory, that's just to set up the notation. For other people, it's not a problem. Just consider integer rectifiable, in a sense, integral currents as related to classical surfaces as much as Sobolev functions are related to smooth functions. Okay, and you're fine. So far, so good. So theorem, and this is a cornerstone in the theory, where in the case of codimension 1 is due to de Giorgi in the set of finite perimeter sets, but this is a particular case. Okay, and in the setting of general codimension is due to Federer and Fleming. Okay, and this theorem is telling you that there exists an area minimizer or a minimizer for the quantity we define, the mass, so a mass minimizer in the class of integral currents. Okay, so either with fixed boundary or in a suitable topological class, whatever you want. Great, so now, let me see where we are. Okay, so and this theorem here, we achieve it by applying the direct method of calculus of variation, and now you immediately see that the lower semi-continuity is coming basically almost for free, because lower semi-continuity of your quantity, here we are taking the supremum of a family of continuous functionals, which is lower semi-continuous. The problem here is compactness, because actually the first thing you realize is that this space of integral currents is no more a linear space. Why? Because if you take two integral currents, you sum them up and then you are fine. But the problem is that when you multiply them by a real number, they are no longer with integer multiplicity. So you really don't want to talk about square root of 2 of a surface, okay? And indeed, that's why the compactness theorem here is really a geometric theorem and not just functional analysis, okay? Good. So, and that's okay. So a priori, you may have more than one solution. Nobody's telling you that the solution is unique. So just you may have really a lot of examples, but if you just consider two circles and then you take one with one orientation and one with the opposite orientation, if they are far apart, then you know the solution is going to be the two disks. But as long as you push them together at the very end, you're going to get the catenoid, and there is going to be a threshold for which you have two minimizers. Okay, you may construct even easier example, actually. So with this at hand, you can also have fun, and you can also build very exotic examples, and this is what actually Frank Morgan did some years ago. So examples, there are 2 examples by Morgan, okay, and 81, where in the first article, he was able to prove that if I give you in R4 a smooth Jordan curve, then you can actually find a continuum of area minimizing surfaces, which are unoriented. So actually I'm cheating a bit, but still is a nice example. And in the second case, he was able to prove that if I give you a smooth curve in R3, that curve is, which is actually analytic, you can actually prove that you have a continuum of minimal surfaces, so surfaces that are stationary for the area functional, okay? So you can really have fun in doing this, but what I want to pass is that actually you don't have uniqueness. Stationary, minimal surfaces. I said minimizer. Okay, no. Stationary. Well, there is also an example by Bombieri, actually, that is coming out from the article with Giorgi and Giusti, that you can actually do it with also finding countably many in R4, but you do it in the flat Clifford torus and stuff like that, but they are just area minimal surfaces. In R3, there is a theorem actually, so I want to address this because it's nice. There is a theorem by Tommy that is telling you in R3, and coupled with some regularity at the boundary, that if you are a smooth Jordan curve in R3, you cannot, with sufficient regularity C for alpha, okay, you cannot bound more than finitely many curves. So it's a bit delicate in R3, but yeah, so these are minimal, so stationary. Okay, so we realized that we don't have uniqueness in general for these kind of problems. And then the next step that you can ask, okay, I don't have uniqueness in general, but say that I give you a boundary and say that I perturb it a little bit. Am I able to restore uniqueness? And the answer is yes, okay? And now I can state you what we proved, which is a joint work again with M, and S, you can read the names. So for the generic boundary, for the generic boundary gamma, okay, there exists a unique area minimizing integral currents, T, such that the boundary of T is equal to gamma, area minimizing integral current, and moreover, T has multiplicity equals to 1, H, M almost everywhere. Okay, so this is the first part, and this is the introduction. Okay, so if you have any question about that, please ask. Otherwise, I'm going to erase something. No, of course, we have some regularity, but now I'm a bit informal. Well, we have also another result in a different topology with more generic boundaries, but I will be more formal later on in the talk. Now, this is just to tell you the result. Okay, indeed, as I wrote here, you can see I'm taking the current natural induced by something regular. Okay, good. Okay, so now I can start with the second part of the talk, and I need to review some theory of regularity and some previous result about uniqueness of this problem. And okay, so we are happy we solved the Plateau problem, but what we have now is just an ugly integral current that may be, may be far from being a smooth surface. Okay, so the natural question is to ask, okay, from the fact that I am area minimizing, how regular is actually this integral current a posteriori? So regularity theory is dividing into 2 parts. The first one is interior regularity, which is the regularity of the minimizer away from gamma, the boundary. And then you have boundary regularity, which is the regularity of the minimizer close to gamma. Okay, good. So before starting and telling you the results, what I need to do, of course, is to introduce and to tell you what is a regular point. Okay, so definition. A point P is regular if, okay, in the interior case, if P is not in gamma and there exists U neighborhood of P such that the current T restricted to U, and I will explain, is going to be Q copies of this object, okay, where in this case here, sigma is a sigma in U, is going to be a C1 oriented submanifold. Okay, and Q is going to be a natural number. Okay, what do I mean by T restricted to U? It means that if I see the action of the current on forms, then you just see the action of the current on forms that are compatibly supported on U. And if you know that your current is actually an integer rectifiable current, then you just take all these very ugly pieces and you just intersect them with U. Okay, this is just that. Okay, so this is the first definition. And then you have the definition of a boundary point, regular boundary point, which actually we need to distinguish between two cases. The first one is the easier one. The second one I need to explain a bit more. So the first one I will call one-sided. Okay, so you are a regular one-sided boundary point if P is in gamma and there exists a neighborhood P of P such that, okay, T restricted to U is going to be equal to sigma. Okay, but now in this case here, sigma is going to be sigma in U is going to be a C1 oriented submanifold with boundary. So the boundary of sigma intersected U is equal to big gamma. Okay, and this is the natural notion of manifold with boundary that we know. The problem is that actually in this case, we have another possible situation that may happen. That is what is called a two-sided regular boundary point. Okay, and this is a point still in the boundary, and there exists a neighborhood of P such that. Okay, let me write it like something this. Okay, and this is, well, let me cancel this because it's the usual situation that we know. So T, in this case, T restricted to U is going to be two things. The first one is actually Q copies of what I will call sigma plus Q minus 1 copies of what I call sigma minus. Okay, where now in this situation here, sigma plus and sigma minus are two C1 oriented submanifolds with boundary, and how they take the boundary is this. So you take the boundary of sigma plus is equal to gamma, which is equal to minus the boundary of sigma minus. Okay, so let me explain what kind of situation I have in mind, and it is something like this. Okay. Take something like this. Take a curve. This is our boundary gamma. Okay. This is something like this, and this is something like this. This is sigma minus. This is sigma plus. Okay. And they are taking the boundary with opposite orientation. So now you realize that in this case here, this sigma minus is taking the boundary gamma with multiplicity Q minus 1, but negative. Sigma plus is taking the boundary gamma with multiplicity Q, but positive. And since the boundary gamma, they are canceling the sense of currents, at the very end, you just get the boundary gamma with multiplicity 1. Okay, So this is the situation. Okay, so another remark, let me tell you, in this situation here, is that by a simple variational argument, you are able to prove that these two submanifolds must come together at the boundary gamma with the same tangent. Okay, indeed, suppose that this was not the case, then suppose they are coming like transversal, then you are able to take q-1 copies of gamma minus and q-1 copies of gamma plus and pull them down, okay? And just by simple triangular inequality, you have something that is better. And then you satisfy the boundary condition, just taking one copy of sigma plus that is going straight and take the boundary, okay? So if these two are not with the same tangent, then you can, since you are area minimizing, you construct a better competitor, okay? Okay, so this is a remark that I want to say. And okay, okay, good. So now, by this argument that you know that they are coming together joining at the boundary gamma with the same tangent, you realize that actually at a two-sided regular boundary point, what you get is the union of sigma plus and sigma minus, okay? Union sigma minus, which is actually sigma, which is a C1 oriented submanifold without boundary in U, okay? And then, since you are area minimizing, you can write down locally the partial differential equation of the system of partial differential equations of the minimal surface system of the minimal surface equation. And then you can upgrade regularity as much as your ambient manifold is allowing you to do, okay? And so I can just put it here. And this is a remark that I listed here because it will be useful later. Sigma. Sigma could have, well, I mean, you have a boundary, so you are changing multiplicity. But you can be considered as a whole manifold, of course, with multiplicity. Sure, exactly. But here you have a boundary, so you change multiplicity from one to the other. Exactly. Okay, so, but as long as the support is concerned, you can improve regularity. That's the thing, okay? So this same reasoning can happen also, you can do it also for one-sided regular boundary point. The problem here is that you can upgrade regularity as much as not just the ambient manifold is allowing you to do, but also the boundary is allowing you to do. So it is the minimum of the regularity between the boundary and the ambient manifold, okay? Good, so that said is I take it there and I leave it there, okay? Good, so I can cancel something there. So if you have any question, I'm happy to answer I cancel. So if not, I want to tell you that actually this kind of regular two-sided boundary situation can actually occur. So say that I give you these two circumferences that are lying more or less on parallel planes, okay? And say that I orient them in the same way, okay? When they are far apart, you know, well, we know that the minimizers are going to be the disks. And when I stress them together, somehow they are forced to actually go and get the minimizer, the catenoid, but our boundary condition is not allowing the catenoid to form because it would take the opposite boundary. So in a sense, orienting the boundary in the same way, we are forcing the solution to be the two disks. And when we squash them together on the same plane, we are going to end up with something which is a solution of the Plateau problem, of our oriented Plateau problem, which has multiplicity 2 in the interior disk, multiplicity 1 in the exterior corona. And if you are a point in this boundary here inside, P, okay, then you are exactly a two-sided regular boundary point, okay? And notice that this situation is really coming from the fact that we are considering the oriented Plateau problem, because if we were allowed to change the orientation of the upper part, and we take something like this, okay, when they squash them together, they are going to form actually the catenoid as a better competitor. And at the very end, when you go down, you see that the minimizer is just going to be the outer corona taken with multiplicity 1, and then the point P of there is just going to be a one-sided regular boundary point. Okay, good. So now, okay, with all said, I can go and recall some results about the regularity theory for integral area minimizing currents. And the first thing I need to tell you is that regularity theory really depends on the codimension you're working in, okay? So in codimension n equal to 1, okay, what you can prove is that the set of interior singular point of your area minimizing current has Hausdorff dimension at most m-7, okay? So the set of interior singular point is what you can understand. So it is the set of points in the support of the current which are not regular, singular, which are not at the boundary, so interior, okay? And this result came from a joint effort of several mathematicians in the 60s. So you start with the Giorgi, Fleming, Almgren, Simons, Federer, and then you can also say that the singular set has a nice structure. So it is actually rectifiable, and is a result by Leon-Simon, and it is actually has locally HM-7 measure, and this is a result by Naber and Valtorta. Okay, so far so good. So at the boundary, and let me call this something like this, the set of singular point of the current is actually empty. Okay, good. And for this, of course, I need to consider a regular boundary point, both a one-sided and a two-sided boundary points. Okay, and this is a result which is due to Hart and Simon, and at the end of the 70s. Okay, and it is a very nice result. Okay, and these results, of course, these not are sharp. Okay, good. In codimension higher than 1, okay, higher than 1, it took almost 15 years and a typewritten manuscript of 1,728 pages to Frederick Almgren to prove that the singular set, the interior singular set of an area minimizing current in higher codimension, has Hausdorff dimension at most m-2. Okay, so this is Almgren, 82, and then Delellis and Spadaro, 2011 till 2016, with a series of 5 articles where they understood, simplified, developed new theory to be able to actually prove this bound and actually go further with the theory. Indeed, it is just as a recent result by some months ago that actually Delellis, Minter, and Skorobogatova proved that actually the same result of Leon-Simon codimension 1, so actually you have a rectifiable structure of this set, can be proven also here. And there are some announcements by also Kramel and Vikramasekera that actually are proving the same thing, but also with the bound on the Hausdorff measure. Okay, but still one article is missing. So okay, and an important remark that I want to make here is this one. So this bound here is very important because it implies that the HM-1 measure of the interior singular set of an area minimizing current is 0. So this is important because what I'm telling you is that in general higher codimension, if your integral current that is area minimizing and is solving the Plateau problem is actually regular outside of a very, very small set that cannot disconnect the regular part. Okay, and this is something that is going to be useful. Okay, so boundary. Okay, so at the boundary, nothing was known before a very long and great article by Delellis, De Filippic, Hirsch, and Massacesi in around 2017, 2018. That was actually very general and was actually working in the setting that I wrote at the beginning. And before their article, in the very general setting that I sketched at the very beginning for the oriented Plateau problem, you were not able to even tell that you had just one regular boundary point. Okay, so a priori you could have singularities in the whole boundary. Okay, and there were just some partial results that actually are dating back to the PhD thesis of Allard. Okay, that are actually, okay, let me write it here. Actually, Allard proved this theorem twice. Okay, he proved it for area minimizing integral currents in his PhD thesis, And actually, he proved it also for more general objects, stationary varifolds. Okay, so we can write something like this. Okay, and what Allard is telling you is that if you take your ambient manifold m plus n to be the Euclidean space, okay, and if you assume that your boundary gamma is lying in the boundary of a uniformly convex set, then you know that you're regular. So the set of singular points at the boundary for your area minimizer is going to be empty. Okay. So how can you, okay, let me call it this one star. So how can you understand this condition here? So this condition here is telling you that actually you can form some kind of convex, uniformly convex barrier around your boundary gamma. And from some simple convexity argument, you can actually prove that your minimizer T is lying inside your uniformly convex set. So the condition you want, you get actually from this assumption here, is that you are ruling out a priori the formation of two-sided regular boundary points. Okay. So, and then Allard concludes that with this condition, you can prove that you have density 1/2 of the boundary, so you're regular. Okay. Good. So the first remark here is that actually this condition star is ruling out two-sided irregular boundary points. And the second remark is that this condition here, that actually seems to be a global condition, because you're asking a condition of the whole gamma, has been localized in an article by Hart in the 77. Okay. So as soon as you are able to find this condition, uniformly condition here, so a uniformly convex barrier at a point at the boundary, then you can apply this result. Okay, good. So now this is okay. Okay, so it is now that it is now relying on this boundary regularity theorem that Frank Morgan was able to prove some results about generic uniqueness of area minimizing currents. Okay, so let me write something like this. So Morgan, and it is 78, 81, and 82. Okay, so let me summarize the main ideas of Morgan. Okay, so the first result of Morgan is that, okay, let me write something like this. Under condition star of Allard, then almost every curve gamma in R3 bounds a unique area minimizing currents, bounds a unique T area minimizing currents that is taking the boundary gamma. Okay. Now, two, the set of curves of gammas, okay, the set of curves for which there exists a unique area minimizing current T, okay, unique area minimizing integral current T, is residual. Where for residual, I mean in the sense of their categories. So a set is residual if it contains a countable intersection of open dense sets. Okay, good. So some remarks. First one, Morgan always worked under the assumption of Allard. Okay, so under always the assumption of finding this uniformly convex barrier. The second one is that Frank Morgan was working where in a setting where the ambient manifold was the Euclidean space. Okay, R3. Actually, it is not very important the 3-dimension. You can also increase the dimension, but what is important is that you keep codimension 1. Okay. So this is the first remark. The second remark, it is, what does it mean almost every? Okay, so almost every means that you have to construct a geometrically meaningful measure. And this is actually the difficult part of the paper. Okay, so what do I mean by geometrically meaningful? Means that this measure that you construct, okay, on the space of curves, is giving positive measure to open sets of curves first, and then you have some conditions like this measure is invariant under rotation in the Euclidean space, and somehow also translations. Okay, good. Okay, so that's fine. Now, let me tell you the proof of the second part of Morgan. Okay, so if you have any question, I'm happy to answer. Otherwise, I will give a proof by drawing, which is, and actually this is a very nice idea. Okay, proof of 2. It is an idea of Angren. Morgan says, okay, so, okay, by assumption, you know, because you are under hypothesis star, you know that you have a one-sided regular boundary point. So assume this is not a big deal. Assume that you have just one connected component. Then sure, please. Residual means in the sense of bare category. So you can just think about being topologically large. I will be a bit, if I have time, I will be a bit more precise on that because I will try to explain. But first, think about topological large in the sense of topology, because you know that you can construct in the real line a set, you can partition the real line into a set that is a complement of a residual set and a set of measure 0. So these two notions are actually not compatible in a sense. To be able to say you are large in one sense, you are not maybe compatible with being large in the sense of measures. Okay, so Morgan was able to prove two things: that the set is large in the sense of measures for his measure, and also in the topological sense. So technically speaking, residual means that you contain a countable as you are a set is residual if in a topological space you contain a countable intersection of open dense sets. Okay, if you are in complete metric space, then you can also say that you are dense. Okay, okay, so but thanks for the clarification because it is important. So we are under assumption star, so you know that you have a one-sided regular boundary point. So what you do is that you pick it, and then you know that around here, and again, without loss of generality, consider just one connected component, can be done this perturbation in every connected component. You know that here, your boundary gamma, your area minimizing current T, here is actually regular, okay? So what you do is that you take a very tiny perturbation of your boundary gamma and you go a bit inside the support of the current where you know you're regular. So you do something like this. Okay, here is the original boundary gamma, and here is gamma prime. Here is your point P, and now you define this gamma prime entering a bit with a small perturbation inside. And then you take a minimizer T prime, which is actually the restriction of T. And see, since you are the restriction of a minimizer, you are the minimizer for the new boundary. Okay, so what you do is that you want to find the uniqueness for this new boundary, okay, for this new perturbation. So you suppose that you have another minimizer S prime that is taking this boundary here, and it is area minimizing. But then what you do is that you suppose that you come, well, okay, what you prove is that you are at this part here. I don't know if there are colors, actually, let me see. Oh, there are colors, nice. Okay, so at this part here, you prove that your minimizer S prime has to come tangentially to that part, because if it is not coming tangentially, then what you do is that you add back this part here you removed, and you go back to the previous boundary gamma. Okay, and for the boundary gamma, T prime plus this part here is actually T, and you're a minimizer. But then what is also minimizer is S prime, the new minimizer, plus this part here. Okay, but then you suppose by contradiction actually that you have this whole line of singularity because you are coming transversal. But they're going to arrest us because there is Amgren and Deleuze Spandaro that are telling us that the singular set cannot disconnect the regular part. Okay, good. So at the end, you find uniqueness for this new perturbation. Okay, and this is the argument of Morgan. Okay, and so remark, as long as you are able to find a one-sided regular boundary point, that you can apply Morgan's machinery. Okay, good. So if you have any question about that, okay. So the problem here is that, again, before 2017, nobody was able to tell you that you could even find in general codimension even just one regular boundary point, okay? Nobody but the Lelis, the Filippis, Hirsch, and Massaccesi. And so now we recall their theorem. Sure. No. Yes. Yes, exactly. There are some arguments, and we also do this argument that in particular, in general, you cannot say that if you're dense, you are residual. Okay, that's true. Take the rational numbers. But in our case, well, there is a simple argument that is telling you that if you assume that you are dense, in our situation, then you can prove that you are also residual. So actually, this is a nice remark because indeed, in our situation, and actually in a situation like this one, like the one for Morgan, it is enough to prove you are dense to be able to say that you are residual. So it is an if and only if in this situation. Yeah, and it's pretty nice. Yes, yes. Yeah, you assume that you are dense. You discretize the set of boundaries that have not uniqueness. You write it as a countable union of sets, and you prove that these sets are closed because they are also with empty interior because you started with the assumption that you are dense. And then you can prove that they are closed under a suitable topology, and then you are residual. So actually, yes, but the idea is actually, I didn't want to go into this, but it's a nice remark. Exactly, thank you. Okay, so far so good. Okay, so now, okay, there is this theorem that is De Lellis, De Filippis, Hirsch, and Massachesi, okay, that is telling you, okay, no, I cannot do this, okay, so let M plus N be a C3 alpha Riemannian manifold, which is complete, okay, let, I don't know if you can see, otherwise I go there, let gamma M minus 1 dimensional submanifold of your ambient space, and you know that you are oriented, and you know that you are a boundary in integral homology, then what you do is consider the area minimizing currents associated to this boundary. So let T be an area minimizing integral current for your boundary, okay? And okay, sorry, this is of the same regularity, C3 alpha regularity, okay? Then let me summarize their result, their main result. You know, first thing, that the set of regular boundary points of the current T is dense, provided that you consider one-sided and two-sided regular boundary points. And so this is a relatively open, in the support of the current, open set, and it is dense. Okay? Second result, they have a structure theorem, which is telling you this. Call gamma I a connected component of your boundary gamma, okay? If gamma I contains one-sided regular boundary point, then the whole set gamma I intersection reg B of your current is all one-sided. Okay, so as long as you find one in the connected component, that all of them, the regular ones, are one-sided. Moreover, you can prove that, well, calling it Ti, the part of the area minimizing currents restricted to the connected component, this one has multiplicity 1 almost everywhere. Okay, good. And this part here holds also for two-sided regular boundary points. As soon as for a connected component, you can find a one two-sided regular boundary points, then all of them, the regular ones, are two-sided. Okay, good. So you understand now that if you can tell me that generically, in a generic situation, in the sense of bare categories, but generically, you just see one-sided regular boundary points, then you are able to say, by the structure theorem of them, that the area minimizing current, okay, you could consider different connected component, you find just one-sided regular boundary points. So the area minimizing currents for this boundary has multiplicity 1 almost everywhere. Moreover, since you just know that you have just one-sided regular boundary points, you can apply Morgan's machinery and say that the solution of the Plateau problem is unique. Okay, and this is exactly our strategy. And this is leading me in the last 10 minutes to the part 3 of the talk. Okay, so if you have any question. Okay, let me do it here. Sure. Okay, let me write, but you mean, okay, well, boundary interior is not the same. So Amgren did it for C5 regular manifold. They did it for C3 alpha. And actually you need C3 alpha because when you build a particularly difficult object that is called this, but I mean, if you have this question, you know, the center manifold, okay, then you need C3 alpha to be able to allow some decay of Amgren's frequency function, okay? So honestly, honest answer, I don't know if actually you can gain something, if it is sharp, okay, in the construction, but this is due to the construction of the center manifold, which is pretty complicated. And it is still a nice improvement, I would say. You go from C5 to C3 alpha, and it is a nice also PDE article, but okay, so about their result, there is C3 alpha. So yeah, I don't think you can improve, but I don't, yes, I don't want to say things that I don't know actually. So, okay, good. So part 3, but for, yeah, okay, fine. Okay, so part 3, I need to tell you, okay, our results, okay? So let M and M plus N dimensional complete Riemannian manifold, okay? Let gamma an oriented, closed, for technical reasons, but closed submanifold, which is a boundary in integral homology, okay, of class, okay, this is of class C3 alpha, and this is of class, sorry, this is of class C3 beta, and this is of class C3 alpha, where we have 0 strictly smaller than alpha, strictly smaller than beta, okay? Then what you can prove is that the generic perturbation of class C3 alpha, where for perturbation, I mean the boundary that you get perturbing the original boundary, the generic C3 alpha perturbation admits, so there exists a unique minimizer T, okay, such that the boundary of T is equal to this one. And moreover, T has multiplicity 1 almost everywhere. Okay, good. And this is our result. Okay, so in the last minutes, let me tell you something. Okay, so how you prove, what is the general idea? Now it should be kind of clear in the sense that I told you that there is this difference between one-sided and two-sided regular boundary points, for which for two-sided regular boundary points, you can improve the regularity around them as much as your ambient manifold is allowing you to do. While for one-sided regular boundary point, you can just get the minimum of the regularity of the boundary and your ambient manifold. So you understand that your aim, as I told you, is to be able to say that generically, in a generic situation, you only find one-sided regular boundary points. And this problem can be translated as saying that the generic curve, the generic C3 alpha curve, is not lying in a C3 beta manifold, where beta is a bit more than alpha. Okay, so all amounts to prove the following proposition. Okay. Okay. Proposition. The generic M-1 dimensional C3 alpha graph, okay, and now we are in our M plus N, okay, where for graph, I consider the graph of the perturbation, so the graph of the perturbed boundary. The generic n-1 dimensional graph is not lying in any C3 beta submanifold. Okay, so as long as you're able to prove this, then it's just technical machinery to be able to transfer this proposition here in the space of integer or in the space of integral boundaries. And as soon as you know that this is true and you put it there, you're able to prove that you don't have in a general situation two-sided irregular boundary points, and then you can apply this structure theorem and Morgan's machinery to be able to prove the result. Okay, good. So I have still 5 minutes, and I'm happy to have these 5 minutes, because in these last 5 minutes, I know that I'm the last talk, so I should say, okay, stop. But if you are okay, I will go on 5 minutes. And I want to spend these 5 minutes to be able to tell you more precisely what does the word generic mean, because I never define it really rigorously. Okay, so first of all, okay, just let me recall, I don't want to write it, otherwise it takes much more time. So, well, if you have X, which is a topological space, okay, this is just some definitions, okay? X is a topological space. We say that F is a subset of X, is a set of first category in X if F can be written as a countable union, okay, of sets which are nowhere dense. So sets whose closure has empty interior. And this is a set of first category. We say that a set is residual in the space X if it is the complement of a set of categories. So if it can be written as a countable intersection of sets whose interior is dense in the space. Okay, so I know Mattia is a bit different from what I told you, but it's equivalent. Okay, so di where int of di are dense. That's okay. Good. So rigorously, I say that a property P is holding for the generic element if the set of elements for which that property holds is a residual set. Okay, this is the formal definition. Okay, so there is a theorem, okay, which is telling you that if you are in a complete metric space, then a residual set is dense. Okay, this is what I was telling you before. So now with this theorem, you can actually prove that, well, you can understand that some works that we have to do, which is actually not the most difficult part, is that you want to construct a suitable, okay, complete metric space of boundaries. Metric space of boundaries. So the first part is that you actually want to construct this complete metric space of boundary, which is actually not so difficult. And then what you want to prove, what you want to define is this set here, calligraphic A, okay, that let me write it like this. This is the set of C3 alpha perturbations, so perturbed boundaries, okay, for which there exists a C3 beta submanifold N, and their graph is actually lying in it. Okay, so this is the set of C3 alpha perturbation for which there is a more regular submanifold for which their graph is living inside. Okay, and the main strategy is to prove that this set here is of first category. Okay, once you have proved this, then the complement is residual, and then you can go back and prove the whole machinery. Okay, and in the last 1 minute and 20 seconds, I will tell you that the way we prove this, okay, is actually a very old strategy that will go back to Mazur first and proved by Banach, which is called the Banach-Mazur game. Okay, it is very old, but is actually, for what I've seen, the first time that has been applied to this kind of literature. Okay. And there is, I don't want to rigorously define what a Banach-Mazur game is, not because it is difficult, but because I don't have time. So if you're interested afterwards, just tell me. But there is a theorem that is telling you this, that if X, your space, is a complete metric space, then is a game, so there are two players that are playing, that one of these two players has what is known as a winning strategy if and only if, okay, a particular set is of first category. Okay, so of course I understand that I should define what a Banach-Mazur game for a particular set is, but this is the last part of the talk, so let me go a bit fast for people that already have in mind this. So all boils down to prove that in this situation you actually can construct a suitable winning strategy. Okay, and yes, so yes, I would. Okay, I don't enter into many details because my time is over, but if you are interested in something more, I'm here to tell you. So I thank you for your attention, and this was all.
Okay, first question, you know what I have to ask.
Please.
Any improvement in the direction of Steiner problem?
Okay. Yes. Okay. So first of all, a bit of context. Okay, we have another result actually that is proving generic uniqueness, not multiplicity one, because in that case you don't have it. But we are proving generic uniqueness for a different topology, not the C3 alpha. That actually can be proved to CL whatever. Okay, but in a weaker topology, that is the flat topology. Okay, for those of you that know the flat norm in the sense of currents. And this allows you to actually prove generic uniqueness for a very large set of boundaries. Okay, and okay, so this in this setting it is actually a bit cheating, but it turns out that to be able to, I mean, the flat distance is a natural quantity, a natural notion to be able to consider problems in optimal transport, in a suitable class of optimal transport that is called optimal branch transport, okay, which can be formulated in a formulation with the theory of normal currents, okay? And in that setting, you can prove generic uniqueness, okay? And with a kind of perturbation, okay, which is somehow similar to what we do in that setting, but you are in a completely, you encounter a completely different problem that is this one. You don't have anymore something like this. Okay, so think about, okay, so think about area minimizing, well, think about currents with coefficient in an abelian group like mod P, okay? You know that there is a result by the Lellis, Hirsch, Marchese, Hirsch, and Stuvard, okay, 2020, and they tell you that the singular set in any codimension, any dimension, and whatever, is at most of household dimension m-1. So actually, in that situation, the singular set can disconnect the regular part of your surface, right? So if you're asking me any improvement about the Steiner problem, okay, somehow the first question is actually, okay, can you find some way to prove generic uniqueness when you have singularities that can actually disconnect the regular part? And this is actually a nice problem because I don't know if generic uniqueness has been proved for mod P currents, for example. It would be nice to apply the strategy for optimal branch transport, maybe in that setting. That would be something that we may think of. Another thing is that actually what we do in the optimal branch transport is that we are proving for a range of exponents, okay, that is actually not tackling the Steiner problem. And yes, there are issues for the Steiner problem, okay. For example, okay, in that article, we are working a suitable class of boundary that have bounds on the mass of the current and on the mass of the boundary. And if you do perturbation for the Steiner problem, you actually escape that boundary. So this is the first problem. We actually wanted to prove that, do the vice versa, prove generic uniqueness for transport, branch transport, so encompassing also the Steiner problem with this kind of uniqueness continuation. You take one solution, you enter it a bit, and then you actually find just one solution for that boundary. But it turns out that there is this problem of singular set that is so big that actually you cannot control the topology inside, okay? And I don't know. Yes. So no, no good news and no novelties in that situation. But I hope that something can be done in this direction. Yes.
Other question?
I have maybe a very dull question, but I don't have
Sure.
by now a feeling about this notion of genericity.
Okay, sure.
Is it your result of genericity? Is it stronger or weaker than the one I have in mind? That is, if you perturb with a
The metric.
Okay. Also, this is a question, but also if you perturb the C3 alpha graph with a C3 alpha perturbation, do you get
Okay, perturbing with the C3 alpha perturbation, you are actually proving a denseness result, as he was saying. Okay, and there is a lemma inside that is telling you that if you are able to prove that you are dense, then you are residual. So actually, in general, it is stronger, but in our case, it is actually equivalent.
Okay, so if you take a graph, you don't know if you have uniqueness, but if you perturb the graph with a C3 perturbation,
yes,
you have uniqueness for these perturbations.
Well, under our assumption,
yeah,
sure,
fine,
sure.
Okay, and the other one was about the metric on the ambient. If you can perturb the metric in order to get the generic existence.
So yes, okay. So there are results in this way, and they are used when you want to work in the homological Plateau problem. Okay, so say that you want to minimize and find an integral current in a suitable homology class, or homotopy class, or cobordism class, or whatever you want. Okay, take the homotopy class. Then what you do is something that you don't have the boundary, right? So you cannot do our trick, Morgan's trick. Okay, so what you do actually is that you perturb the metric, the ambient metric, okay? And so you get a genericity result in the sense that you perturb a bit the metric, and actually it is exactly what it is done in a lemma, okay? I don't remember which lemma, but there is an article by Chodos, Mantulidis, and Schulze, okay, where they are actually proving generic regularity for codimension 1 area minimizing currents in dimension, well, 8, 9, 10, exactly. And what they do is that they do also the homological version, and at a certain step, what they need is a generic uniqueness of the solution. And in the homological setting, they do exactly a perturbation of the metric of this type, of the type you have in mind, okay? And there are many ways to do it. And okay, there is one more difficult way, but actually there is one way that goes back to an article by Smail, okay, in the whatever, okay, which is proving homological generic regularity for homological mass minimizer in dimension 7, okay, the first layer, okay, and it is just a conformal change of the metric, and a conformal change of the metric is actually allowing you to do this trick of entering a bit inside. It's not more complicated than that.
Okay, but the argument can be concluded with this very trick here of the Mazur trick, or the conclusion is different. Is there a relation with this
okay, stated like this?
Can we implement this picture to the genericity in terms of the metric?
Okay, we didn't discuss the argument of the metric. Okay, so we are just considering the manifold. We don't even put the metric in that. We just do this. But I mean, sure, it may be done. It is holding for any metric, okay, as long as you have a bit of regularity of the metric, because you just take your package, okay, you ask that, okay, your metric is C4, okay, you embed everything, okay, you derive your results, okay, and then you go back. So all our results, generic uniqueness and generic multiplicity, hold for any metric, and you can do this perturbation for the metric.
And find the genericity in terms of the perturbations of the metric.
It would be not, okay, so not trivial, because if you want to do exactly the same strategy, then you want to write down the Banach-Mazur game and do all this stuff. And our perturbation is really actually a perturbation that is taking one direction, and this connects to some question. But in one direction, you do a bit of a bump to be able to say that your C3 alpha function is actually not C3 beta. Okay, so we are actually really playing with graphs, functions, and stuff that are entering inside. Of course, you need to translate everything into metric, but sure.
Fine, and sure. Thank you. Okay.